In the darkness of space, a solitary star burns with a gentle fury. This is our Sun, the radiant heart of the solar system, an immense sphere of glowing plasma that anchors worlds in its gravitational embrace. Its light is the daymaker, shining across the void to illuminate the planets. At this distance, we cannot hear the tumult of its nuclear fires. We feel only the steady warmth and life-giving glow that has nurtured Earth and its neighbors for billions of years. Deep within the Sun's core, hydrogen atoms fuse into helium, releasing energy that travels outward over millennia before escaping into space. This energy is the Sun's enduring gift, radiating from a seething surface that has no solid ground, just a sea of luminous gas. Above it, a pearly white corona unfurls, strangely hotter than the surface below, a mysterious halo of million-degree plasma visible only during eclipses. The Sun's face is often freckled with dark sunspots and prone to sudden flares, magnetic storms that remind us this star is dynamic and alive. Yet from afar, our star appears calm and steadfast, a warm beacon in the emptiness. For roughly 4.5 billion years, the Sun has burned in cosmic solitude, circled by the tiny specks that are our planets. It contains almost all the mass of the solar system, truly the gravitational anchor around which everything orbits. Over 1 million Earths could fit inside this stellar giant, and its gravity guides the paths of worlds, asteroids, and comets alike. Every 8 minutes or so, a photon leaving the Sun's surface reaches Earth, bridging 150 million kilometers of space to bring daylight and warmth. The Sun's energy drives the winds and weather of our distant blue world and paints our skies with dawn and dusk. Though the Sun appears steady, it is far from tranquil. Magnetic fields roil its surface and occasionally unleash titanic flares and eruptions of charged particles. These coronal mass ejections hurtle across the solar system, and when one reaches Earth, our skies come alive with auroras, shimmering curtains of green and red light that dance in the polar night. Such displays are beautiful reminders that our gentle Sun has its tempests, and that even across millions of kilometers, its touch can stir the air of a far-off world. We drift closer, feeling the Sun's presence intensify. The sunlight here is blinding, space flooded with brilliance. Invisible yet potent, the solar wind, a stream of charged particles, rushes past us, carrying the Sun's influence far into space. It is a ceaseless outflow, shaping planetary atmospheres and carving tails from passing comets. In all directions, the Sun's light and wind extend a domain that will eventually fade into interstellar night. But here near the source, their force is undeniable. It is as if the Sun's very breath surrounds us. As we leave the vicinity of our star's blinding glow and venture outward, we encounter the first planet on our journey. Mercury, the Sun's scorched messenger. This tiny planet clings closely to the Sun, so near that from Mercury's surface the Sun would loom more than 3 times larger than it does from Earth. Daylight, there is an assault of brilliance and heat. The rocky ground sizzles under a sun that dominates a black sky, pushing temperatures high enough to melt lead. There are no clouds to soften the glare, no air to carry sound, just a silent, airless world locked in the Sun's unforgiving gaze. Mercury's surface is a battered record of cosmic history. Countless craters blanket the grey terrain, remnants of ancient impacts. Among them lies the colossal Caloris Basin, a crater so vast it spans a quarter of the planet, a testament to the ferocity of past collisions. In appearance, Mercury looks much like our moon, a desolate, pockmarked landscape where each sunrise comes only after weeks upon weeks of darkness. Mercury rotates very slowly, and a single day-night cycle lasts an excruciatingly long time, about 176 Earth days. For half that time, the sun's relentless light bakes one side of Mercury in searing daylight. Then, as the planet turns away, 15 weeks of night plunge the land into deep freeze. Surface temperatures swing from roughly 430 degrees Celsius in the day down to 180 degrees Celsius at night, the most extreme range of any planet. The ground, cracked and dust-laden, endures this endless cycle of fire and ice. Speed is Mercury's defining trait. It races around the sun faster than any other planet, completing a year in just 88 Earth days. In ancient times, skywatchers named it after the swiftest of the Roman gods, and indeed Mercury lives up to the name, forever hurrying along its tight inner orbit. As it speeds through space, Mercury also wobbles in a peculiar dance. Its day and year are locked in resonance. Mercury spins on its axis exactly 3 times for every 2 orbits around the Sun. This celestial rhythm means that if you stood on Mercury's surface, you would witness a bizarre spectacle. The Sun might rise, then pause and dip below the horizon, only to rise again. A double sunrise caused by Mercury's unusual orbital dance. Time and daylight behave in strange ways on this little world. Despite being so close to the Sun's furnace, Mercury holds a few secrets in shadow. In the depths of craters near its poles, where sunlight never reaches, lie deposits of water ice that have likely survived for eons in perpetual darkness. These frozen patches, discovered by radar echoes, are stark contrasts to the blistering heat just a few kilometers away. It is a strange thought that even on the solar system's hottest little planet, ice can find refuge in the eternal night of crater floors. There is essentially no atmosphere here, only a tenuous exosphere of atoms blasted off the surface by solar radiation and micrometeoroids. Without a substantial atmosphere, Mercury is exposed. Its ground is directly bombarded by meteoroids and by the full brunt of the solar wind. Yet, against the odds for such a small planet, Mercury possesses a global magnetic field, a miniature version of Earth's magnetic bubble, though much weaker. This hints at a colossal iron core within Mercury that makes up most of its bulk, a metallic heart that generates a magnetic field and hints at an unusual origin or history for this tiny world. Moving on from Mercury's barren, baking surface, we carry the stark image of a world at the edge of survival, forever scorched by its star. Our path now leads us outward to the second planet, one cloaked in thick clouds and hiding a hellish secret beneath its veil. We set our sights on Venus, the veiled furnace of the solar system. Emerging from Mercury's glare, Venus appears as a brilliant ivory beacon ahead. In Earth's sky, Venus shines as a radiant morning star, or evening star, the brightest point of light after the sun and moon. Up close, however, its beauty is deceiving. Venus is wrapped in perpetual cloud, a dense, yellow-white blanket that hides its surface completely. Contrary to the serene, pearly appearance of those clouds, beneath them lies an inferno of unparalleled intensity. This world is the same size and composition as Earth's, often called Earth's twin, but it has become a toxic hothouse, a twin gone terribly wrong. The air is thick with carbon dioxide, the ground hot enough to melt lead, and clouds of corrosive sulfuric acid swirl endlessly above a landscape of volcanic rock. As we descend in our imagination through Venus's cloud layers, the air grows hotter and heavier with each kilometre. The atmosphere, almost entirely CO2, traps the sun's heat in a runaway greenhouse effect. The deeper we go, the more the temperature climbs, until finally we reach a surface broiling at about 465 degrees, over 860 degrees. Venus holds the title of hottest planet in the solar system, hotter even than Mercury, despite being farther from the sun, because its thick atmosphere lets heat in and will not let it out. The pressure at the surface is crushing, over 90 times the pressure at Earth's sea level, equivalent to being nearly a kilometre underwater on Earth. In these conditions, water cannot exist. Any ocean Venus may have possessed billions of years ago has long since boiled away. The ground is dry and scorched. If we could stand on the surface and survive, we would see the landscape under a dim orange sky, the sunlight diffused by clouds. The terrain is a vast volcanic plain with towering mountains and rolling highlands. Volcanoes dot the surface, some perhaps still gently oozing lava, and the ground is fractured by ridges and troughs. The air around is a caustic haze, often lit by flickers of lightning within the clouds. Venus's atmosphere hosts frequent electrical storms that crackle above the shrouded surface, an angry reminder of the planet's immense energy. Time behaves strangely on Venus. The planet spins extremely slowly. A Venusian day lasts longer than a Venusian year, and it spins backwards, with the sun rising in the west and setting in the east. One full rotation takes 243 Earth days, while a trip around the sun takes only about 225 days. As a result, from one sunrise to the next on Venus is about 117 Earth days. Not that one could see the sun itself from the ground. The thick clouds ensure that daylight on Venus is a perpetual murky twilight. The sun's light struggles to penetrate the sulfuric curtain, leaving the surface in a perpetual dim orange gloom. If you stood on Venus, you'd see a hazy glow all around, rather than a direct sunrise or sunset. And during Venus's incredibly long night, the darkness is near absolute, yet the heat barely relents, trapped by the atmosphere. Venus has been called the goddess planet, named for the Roman goddess of love and beauty, but the name belies its true nature. It is a world of almost unearthly wrath. The qualities that make Earth livable, moderate heat, water, a protective atmosphere, have been pushed past the limit on Venus. Its thick blanket of CO2 has created a choking greenhouse oven. Its clouds rain battery acid. No water softens its climate, and no familiar seasons mark the passage of time. Only an endless, hellish haze. In many ways, Venus is a warning etched in planet form, showing how delicately balanced a habitable world might be. We leave this veiled furnace behind with relief, our spacecraft buckling under the intense heat and pressure in our mind's eye. Out of the acid skies of Venus, we step into open space again, heading toward the third planet from the Sun, our home, Earth, and its faithful companion, the Moon. Almost immediately, a welcome sight greets us. A radiant blue sphere suspended in the darkness, marbled with white clouds. After the barren orbs of Mercury and Venus, Earth is a vision of colour and life. White swirls of cloud dance over the turquoise of vast oceans and the emerald and brown of continents. Polar caps shine brightly at the top and bottom. From space, Earth truly looks like a living jewel, the blue planet, unique in its vibrancy. Earth orbits at just the right distance from the Sun for liquid water to exist plentifully on its surface. And water is everywhere. Immense blue oceans blanket the majority of the globe, regulating climate and nurturing life. A delicate atmosphere of nitrogen and oxygen wraps Earth, providing air to breathe and shielding the surface from harmful solar radiation and meteoroids. Beneath this protective sky, an incredible diversity of life thrives, from lush rainforests to arid deserts, from deep ocean trenches to snow-capped mountains. Our planet's surface is ever-changing, yet remarkably gentle compared to its neighbours. Daylight is warm, but not scorching. Our distance from the sun ensures a Goldilocks comfort. At night, Earth cools, but the atmosphere and oceans retain enough heat to keep temperatures within a range that living things can endure. In this temperate balance, life has flourished for more than 3.5 billion years, transforming the atmosphere by adding oxygen and painting the land with green vegetation. Earth is not just a planet of rock and water, it is a cradle for life, the only one we know. Yet Earth does not travel alone. The planet is accompanied by a single, large moon, a silent grey guardian in the sky. The moon orbits Earth at a distance of about 384,000 kilometers, taking roughly 1 month to complete a circuit. In stark contrast to the blue brilliance of Earth, the moon is a barren, airless world. Its surface is covered in craters from countless impacts and vast plains of solidified lava called maria, which early astronomers mistook for seas. Without an atmosphere or liquid water, there is no weather to erode or change the lunar landscape. Footprints left by astronauts half a century ago still lie undisturbed in the dust, and will remain for millennia. The moon hangs in the black sky, glowing softly with reflected sunlight. The same gentle moonlight that has guided and inspired humans for as long as we have looked upward. The moon's influence on Earth has been profound. Its steady gravitational tug stirs our planet's oceans, creating the rhythmic rise and fall of tides. These tides may well have played a role in the advent of life on land, providing nutrient-rich coastal pools that challenged life to adapt from sea to shore. The moon's presence has also helped stabilize Earth's rotation axis over geological timescales. By keeping Earth's tilt steady at about 23.5 degrees, the moon prevents wild climate swings that could occur if our axial tilt chaotically varied. In this way, the moon has acted as a regulator of Earth's climate, fostering long-term stability that has been friendly to life. The moon's heavily cratered face tells another tale. It has absorbed many impacts that might otherwise have struck Earth. In the early days of the solar system, the moon shielded young Earth from some of the storm of asteroids and comets flying about. Even today, it intercepts the occasional meteor. Our moon truly earns the title of silent guardian, hanging in the sky as a constant companion through the ages. From Earth's surface, the moon goes through phases, a waxing and waning cycle from new to full, as it shines by reflected sunlight. Its gentle glow has lit night journeys, marked the passage of months, and been a muse for human creativity. For thousands of years, humans dreamed about the moon, told stories of gods and spirits residing there, and used its phases to measure time. Then, in 1969, humans set foot on the moon's bleak, beautiful surface, our first footsteps on another world. Those explorers gazed back at Earth as a distant blue marble rising above the moon's horizon, a sight that underscored both our planet's brilliance and the vastness of space. The Earth and moon, large and small, vibrant and still, together form a unique double world. They journey in tandem around the sun, bound by invisible strings of gravity and history. Reluctantly, we bid farewell to our blue oasis and its silent grey guardian, As we depart Earth, we carry the humbling realization of just how special our home is. Now we venture beyond the inner sanctum of the solar system, leaving behind the warmth and familiarity of the terrestrial planets. We set course for a cold, ruddy world that has beckoned our imagination for centuries. Ahead lies Mars, the quiet, red frontier. A rusty red star in the night sky grows into a planet as we draw near. Mars, the fourth planet from the Sun, comes into focus as a dusty, ochre-coloured globe, smaller than Earth and wrapped in a gauzy orange haze. Nicknamed the Red Planet for its iron-rich soil, Mars has captivated stargazers and dreamers since antiquity. Up close, it is a world of deserts and dunes, craters and canyons, all under a salmon-pink sky. In many ways, Mars appears eerily familiar, with polar ice caps and what look like dry river valleys, yet profoundly alien in its silence. No obvious life stirs on its surface. No water flows in its channels. Mars today is a quiet, frozen desert, a planet seemingly at rest. Touching down in our minds upon the Martian surface, we find it a chilly and desolate place. The air is exceedingly thin, about 0.6% of Earth's surface pressure, mostly carbon dioxide with a touch of nitrogen and argon, offering virtually no breathable oxygen. The sky during the day is a butterscotch or apricot hue, tinted by fine dust suspended in the atmosphere. On a sunny afternoon near the Martian equator, temperatures might climb just above freezing, and you could feel a weak warmth on your suit. But by nightfall, they would plunge far below zero. In winter, especially near the poles, carbon dioxide from the atmosphere freezes into dry ice snow, adding a seasonal layer to the polar caps. Mars has seasons much like Earth does, thanks to a similar tilt of its axis. But those seasons play out with more extreme swings in the thin air. Dust devils, miniature tornadoes, twist across the plains, and at times great dust storms engulf entire regions, or even the whole planet, in a reddish haze that can last for weeks. In these moments, day becomes dusk, and the sun fades to a dim amber glow behind airborne dust. It is an environment both stark and sublime. The surface of Mars is littered with clues that it was once a more dynamic and hospitable world. We see vast, dry channels etched into the ground, sinuous valleys and riverbeds that speak of ancient flowing water. There are alluvial fans and delta formations where water long ago deposited sediments. Billions of years in the past, Mars was warmer and wetter. It likely had lakes, perhaps a northern ocean, and a thicker atmosphere to support them. During that time, Mars could have been more Earth-like, and it's tantalizing to imagine simple life gaining a foothold in those ancient Martian seas. Now, however, almost all the water is gone or locked away. We find it as ice, in the polar ice caps, which shine bright white from frozen water and carbon dioxide, and as permafrost hidden beneath dusty soil at high latitudes. Occasionally, even today, orbiters spot dark streaks on Martian slopes that hint at briny water trickling down in the warmth of summer, only to evaporate quickly in the thin air. Mars today is a desert with memory, a world that recalls a wetter youth in its rocks and minerals, for rovers have found telltale clays and salts that form in water. But on the surface now, water cannot stay liquid for long, and life, if it ever began, clings only, perhaps, in the subsurface niches, or not at all. Despite its quiet present, Mars boasts record-breaking landmarks that dwarf those of Earth. Looming on the Martian horizon is Olympus Mons, the tallest mountain in the solar system. It's a volcano about 22 kilometers high, nearly 3 times the height of Mount Everest, with a base so wide, 600 kilometers across, that an observer on its summit would barely perceive its slopes. Olympus Mons rises gently out of the red plains, its edges defined by steep cliffs that drop to the surrounding terrain. And then there's Valles Marineris, a canyon system that cuts across Mars near the equator. This titanic chasm stretches for 4,000 kilometers long and sinks as much as 7 kilometers deep, dwarfing Earth's Grand Canyon. If placed on Earth, Valles Marineris would span the width of the United States. Standing at the edge of it, one would gaze out into an abyss of pink and golden rock, with layer upon layer of canyon walls vanishing into darkness, perhaps faintly illuminated by dust in the thin air. These features speak of a planet that was once geologically alive, a world that erupted with volcanoes and cracked its crust through tectonic forces. Today, Mars's volcanoes lie dormant, and its internal heat has faded, leaving behind these colossal monuments to a more active past. Mars has 2 tiny moons, Phobos and Deimos, which are more like captured asteroids than our large moon. Phobos, the larger of the 2, is a lumpy, cratered rock only about 22 kilometers across at its widest. It orbits Mars at such close distance, just 6,000 kilometers above the surface, that it whips around the planet in under 8 hours, rising in the west and setting in the east twice each Martian day. If you stood on Mars, you'd see Phobos cross the sky as a fast-moving, irregularly shaped shadow against the stars, sometimes eclipsing the sun in a brief, partial eclipse. Deimos, about half the size of Phobos, orbits farther out and more lazily, taking around 30 hours per circuit. In Mars's sky, Deimos looks like a bright star or a tiny moonlet, never growing large, just a point of light gliding overhead. These moons are dark, carbon-rich bodies, likely remnants from the asteroid belt snared by Mars's gravity eons ago. Over extremely long times, Phobos is spiraling inward. One day it may break apart or crash into Mars, adding a ring or a crater to the planet it now circles. For all its barrenness, Mars remains a frontier that calls to us. It is the most Earth-like planet beyond our own, with day-night cycles, familiar landforms, and polar caps of snow, albeit CO2 snow in winter. We have already sent mechanical emissaries, orbiters, landers, rovers, to roam its craters and plains. They have found tantalizing signs of Mars's watery past in the rocks and soil. We've read the story of a planet that had the ingredients for life, but took a different path than Earth. The question of whether life ever sparked on Mars, even in microbial form, lingers and intrigues us. Perhaps hardy microbes once swam in Martian streams, only to perish or retreat beneath the surface as the planet froze. Perhaps some still survive in salty underground aquifers, dormant until occasional bursts of liquid water revive them. We do not know, but the prospect keeps us searching. And in the not-so-distant future, humans plan to follow our robots, to set foot on Mars's rusty soil, to climb its hills and probe its ancient lake beds for answers. Mars is a silent, patient world, but to us, it is a place of hope and discovery, the next stepping stone into the cosmos. As we lift off from the quiet red frontier, we cast one last look at the dusty horizon under an apricot sky and imagine the day when footprints might join the rover tracks in that sand. Beyond Mars, the solar system opens up into a different kind of realm. We leave behind the inner planets of rock and metal and venture outward across a vast expanse where only fragments reside. Soon, the scattered debris of an asteroid belt surrounds us, fragments adrift between planets. This wide gulf between Mars and Jupiter is populated by countless pieces of primordial rock, the leftovers from the solar system's formation. Once upon a time, there might have been enough material here to form another planet, but Jupiter's immense gravity intervened. Instead of one world, we find thousands upon thousands of minor worlds, the asteroids. Between Mars and Jupiter lies this sprawling celestial frontier. Here drift chunks of rock and metal, from boulders the size of cities down to pebbles and dust. Long ago, early sky watchers who glimpsed these through telescopes imagined perhaps a shattered planet, and indeed the asteroids are rubble, but rubble that never quite assembled into a planet to begin with. Jupiter's gravitational tug kept stirring up the planetesimals in this zone, preventing them from coalescing. The total mass of all asteroids is only a fraction of Earth's moon. Instead of a planet, a belt of broken pieces orbits the Sun, a reminder of both creation and destruction in the early solar system. Despite what Hollywood movies might suggest, the asteroid belt is mostly empty space. Each asteroid is separated from its neighbor by huge distances. Our spacecraft sails through this region, and most of the time, sees nothing but darkness. Occasionally, a lone potato-shaped rock will appear, tumbling end over end, then recede into the distance. If you stood on one of these asteroids, you'd likely only see the pinpoint of another asteroid as a distant star-like dot. Collisions are rare, but over millions of years, they do happen. When asteroids collide, they shatter into smaller pieces. Some fragments get flung out of the belt entirely. A few may wander inward toward the Sun, sometimes crossing Earth's path as meteoroids. When we see a shooting star streak across Earth's sky, it could well be a chip off an asteroid that began its journey here between Mars and Jupiter, now incinerating as it plunges through Earth's atmosphere. Not all asteroids are alike. Many are dark, carbon-rich bodies, essentially cosmic time capsules containing organic molecules and primitive material from the nebula that formed the planets. Others are made of silicate rock, similar to Earth's crust, and some are bright shards of iron and nickel, perhaps the cause of unborn protoplanets, exposed by catastrophic impacts. There are asteroids like Ceres, the belt's lone dwarf planet, nearly 1,000 kilometers wide and massive enough to have become spherical under its own gravity. Ceres even shows evidence of water ice and once active geology. Mysterious bright salt deposits glint in one of its craters, likely left by briny water that erupted from below and evaporated. There's Vesta, a smaller world with huge impact basins and a differentiated interior, source of many meteorites that fall to Earth. There are tiny moonlets that shepherd within the belt, caught in Jupiter's gravitational resonances and forever repeating certain paths. The diversity is extraordinary. 1,000,000 stories in 1,000,000 rocks. Drifting through the heart of the asteroid belt, we pass clumps of rubble slowly coasting along their orbits. Occasionally, our ship might be shadowed by a tumbling stone a kilometre across, pockmarked by craters from ancient collisions. In the silent void, these fragments have circled the Sun unchanged for eons, fossils of the early solar system. Here and there, faint gravitational interactions with Jupiter herd asteroids into groups or families. In one region ahead of Jupiter, swarms of Trojan asteroids share Jupiter's orbit, trapped in its gravity like flies caught in a giant's wake. We continue on, mindful of these drifting relics, but largely undisturbed by them, for space is vast, and the odds of a close encounter are low. As we emerge from the asteroid belt, the sunlight has dimmed noticeably. We have crossed a threshold. Beyond this point, the outer planets hold sway, colossal worlds of gas, liquid, and ice. Looming ahead, growing from a speck to a disk, and finally to an enormous striped globe, is Jupiter, the colossus of clouds and storms. Emerging into Jupiter's realm, we are greeted by a sight of staggering grandeur. Jupiter, largest of all planets, banded in stripes of white, ochre, and reddish-brown. Even from a great distance, its vastness is evident. About 11 Earths could line up across its face. As we approach, swirling patterns in its cloud tops come into view. Bright zones and darker belts wrap around the planet, wrought by jet streams that scream east and west. We notice an immense oval storm in the southern hemisphere, the Great Red Spot, a storm like a crimson eye. This high-pressure vortex has been raging for at least 350 years, observed by earthly telescopes since the 1600s. At present, it's roughly twice the width of Earth and a brick-red hue, although it changes over time. Around it, smaller white oval storms and turbulent festoons decorate Jupiter's atmosphere, painting a picture of a planet in perpetual, boiling motion. Jupiter is a world without a true surface, a gargantuan globe of mostly hydrogen and helium. As we descend into its atmosphere, in our minds, since no craft could survive, the blue sky would deepen and the pressure would mount inexorably. The upper cloud layers, at about 140 degrees, consist of ammonia crystals forming whirls of white. Deeper down, clouds of ammonium hydrosulfide and water take shape, creating the tawny and grey-brown bands. Thunderstorms larger than continents crackle deep in the atmosphere, and flares of lightning, some 100 times more powerful than Earth's, illuminate the cloud depths in brief, ghostly flashes. At Jupiter's poles, curtains of aurora dance in ultraviolet, caused by particles funneled by its intense magnetic field. As one ventures still further down, the gas becomes denser, hotter, and more compressed. Eventually, hydrogen, the most abundant component, is squeezed into an exotic form, liquid metallic hydrogen, which conducts electricity and magnetism readily. Jupiter likely has a core of heavy elements perhaps the size of Earth, but it's buried under tens of thousands of kilometers of fluid hydrogen and helium. Essentially, Jupiter is all sky and no ground, a ceaselessly turbulent realm of cloud and storm, transitioning gradually into ocean-like depths of pressurized, fluid hydrogen. Everything we see is atmosphere, a top more atmosphere. The sheer mass of Jupiter is mind-boggling. It's 318 times more massive than Earth, more than twice the mass of all the other planets combined. Its gravitational influence dominates the outer solar system. In many respects, Jupiter acts as both protector and perturbator. Over the eons, its gravity has diverted or absorbed countless comets and asteroids that might otherwise have barreled toward the inner planets. We have seen dramatic evidence. In 1994, the comet Shoemaker-Levy 9, broken by Jupiter's tides into a string of pieces, slammed into Jupiter's clouds, one after another. Each impact created a giant dark scar and fireball in Jupiter's atmosphere, larger than Earth itself. These scars slowly dissipated over weeks, but they were a stark reminder that Jupiter takes impacts that could have caused catastrophe had they struck our planet. At the same time, Jupiter's gravity can nudge asteroids into new orbits, sometimes flinging them inward. It likely helped populate the asteroid belt and Oort cloud, and it continues to sculpt their distributions. Jupiter is often called the solar system's vacuum cleaner, but it is also a gravitational sculptor, stirring up resonances that shape the orbits of other objects, even from afar. Encircling Jupiter is a veritable miniature solar system of its own, a vast family of moons. At least 80 moons have been discovered around Jupiter, and new tiny ones are still being found. 4 of them, however, are truly giants in their own right, first observed by Galileo Galilei in 1610 with his primitive telescope. We turn our attention briefly to these 4 Galilean moons, each a unique world. Closest to Jupiter is Io, a world of fire and sulfur. Io is slightly larger than our moon, but it is the most volcanically active place in the solar system. As our spacecraft passes by, we see giant volcanoes erupting, spewing fountains of lava and gas. Its surface is a riot of colours, sulfur yellows, oranges, and reds, mottled with black lava flows. Lakes of molten sulfur glow in volcanic calderas. The tremendous gravitational pull of Jupiter and tugs from the other moons flexes Io's interior, heating it through tidal forces and melting its rocks. This trapped heat bursts forth through over 400 active volcanoes. Some plumes shoot so high, 300 kilometers, that they rise above Io's thin atmosphere, raining sulfurous snow back down. Io's tortured landscape is constantly renewed. Impact craters cannot last here, as they are quickly covered by fresh deposits. It's a hellscape, yet strangely beautiful to behold across the void. We watch one plume from the volcano Prometheus arcing into space like a great fountain before falling back in a lazy curtain. Io is locked in a gravitational dance with Europa and Ganymede that keeps its orbit elliptical and its interior churning. It is a world in perpetual geological frenzy. Just beyond Io lies Europa, a smooth, icy moon slightly smaller than our moon. At first glance, Europa is strikingly different from cratered Io. Its surface is bright white and crisscrossed with long, dark lines. These global fractures mar an otherwise young, smooth, icy shell. Hardly any craters are visible. Europa's surface is one of the freshest in the solar system. Beneath that ice, scientists are confident, lies an ocean of liquid water, more water than all of Earth's oceans combined, kept liquid by warmth from Europa's interior. As we glide over Europa's surface, we see great jagged cracks and ridges extending for thousands of kilometers, curving across the moon's face. In places, we glimpse reddish-brown stains along these cracks, possibly minerals or organic compounds carried up from the ocean below. There are patches where the ice has been disrupted, broken into rafts, and refrozen in new patterns, hinting at convective motion below. We realize with awe that under our ship, potentially just a few tens of kilometers down, might swim life in an alien ocean, a dark sea kept warm by the same tidal tug-of-war that torments Io. Perhaps hydrothermal vents on Europa's seafloor feed ecosystems as they do on Earth's ocean bottom. We do not know, but Europa has all the ingredients: water, heat, and likely the right chemistry. It is a prime candidate in our search for life beyond Earth. Farther out, we meet Ganymede, Jupiter's largest moon. In fact, the largest moon in the solar system, even bigger than the planet Mercury. Ganymede is a world of both rock and ice, a bulky sphere with a mottled surface of dark ancient terrain and lighter, somewhat younger regions marked by long grooves. It has polar caps of water frost and a thin whisper of an atmosphere that includes oxygen, though far too thin to breathe. Remarkably, Ganymede generates its own magnetic field, the only moon known to do so, which suggests a metallic core and a dynamic interior. We suspect Ganymede also hides a deep ocean between layers of ice, hinted by magnetic data. As our craft passes over Ganymede's equator, we see its landscape. Heavily cratered dark plains are intersected by brighter, grooved bands, where tectonic activity once resurfaced the land with cleaner ice. Ganymede appears as a world that attempted some geological activity early on, then largely froze in time. It orbits Jupiter at a comfortable distance every 7 days, locked in resonance with Io and Europa. Ganymede's sheer size and differentiated interior blur the line between planet and moon. If it orbited the Sun, it would surely be classified a planet in its own right. The fourth Galilean moon is Callisto, farther out in the cold reaches of Jupiter's domain. Callisto is a dark, heavily cratered ice ball, about the size of Mercury as well. Unlike Io or Europa, Callisto shows no signs of a youthful surface or internal activity. It seems to be a relic from the solar system's early days, its face unchanged for billions of years. As we fly above Callisto's night side, we notice its surface glinting with countless ancient craters, their rims softly bright with frost. One giant impact basin, Valhalla, stands out with concentric rings spreading hundreds of kilometers. Callisto's crust is a mixture of rock and ice, and it's thought that beneath about 200 kilometers of solid ice, there might be a buried ocean as well. Even this dormant moon might harbor a secret sea. If it exists, it's an ocean trapped between layers of ice, not likely interacting with rock, so perhaps less interesting for life. Callisto orbits beyond Jupiter's intense radiation belts, in a quieter region. It doesn't participate in the gravitational resonance of the inner moons, and seems to have avoided the tidal stresses that need Io or Europa. Thus it never melted fully or differentiated much. It is a time capsule from the era of planet formation. As we leave Callisto, we appreciate that each of these 4 moons is so distinct. Io, Europa, Ganymede, and Callisto form a miniature model of assorted planetary processes. Not to be forgotten, Jupiter also wears a subtle adornment of rings. We normally think of Saturn when it comes to rings, but Jupiter too has a ring system, though thin and faint. These rings are made of fine dust, likely ground-up remnants of meteoroid impacts on its small inner moons. Jupiter's rings form a delicate halo that glows a pale reddish colour when backlit by the sun. From our vantage, they are almost imperceptible, overshadowed by Jupiter's enormity and brightness. But as our craft crosses through Jupiter's equatorial plane, we catch the sunlit sparkle of dust grains making up a tenuous ring. It is a gentle reminder that rings are a common adornment in the outer solar system. Having taken in Jupiter's awe-inspiring presence, its restless clouds, its great storm, and its system of bustling moons, we prepare to continue outward. We steal one last backward glance at the giant. The sun here is much weaker than back at Earth, only about 1/25 as intense, but still it casts a whitish daylight on Jupiter's cloud tops. In that light, Jupiter looms as a striped colossus, and its 4 big moons hang like a string of beads off to the side. It is a scene of magnificent scale and grandeur. Now our journey calls us further. We accelerate outward, leaving Jupiter and its family behind, heading into the even colder and darker reaches beyond. Far in the distance, a pale golden pinprick, surrounded by a thin gleam of light, beckons us onward. We set course for Saturn, the majestic ringed jewel of our solar system. Saturn, 6th planet from the Sun, slowly grows from a dot to a creamy sphere girdled by an impossible halo. By the time we draw near, the sight is breathtaking. Saturn is a gas giant like Jupiter, but adorned with the most extensive and brilliant ring system of any planet. The planet itself is a huge globe about 9 times Earth's diameter, but notably, it's also very light for its size, so low in density that it would float in water, were there an ocean large enough to hold it. Saturn's upper clouds are a subdued tapestry of butterscotch and ivory hues. Broad bands and zones wrap around it, but they lack the bold coloration of Jupiter's. Everything on Saturn looks softer, calmer. At Saturn's north pole, we spot something unusual. A six-sided pattern in the clouds, a geometric jet stream forming a cosmic hexagon that rotates along with the planet's 10.5-hour spin. This hexagonal storm, large enough to swallow Earth 2 times over, has persisted for decades, if not longer, a mystery of fluid dynamics in Saturn's atmosphere. Apart from such features, Saturn's face appears placid, though in Saturn's deep atmosphere, storms and currents surely rage, occasionally breaking through as temporary white spots or subtle swirls. It is the rings, however, that dominate our view and our imagination. Saturn's rings span over 250,000 kilometers in diameter, but are incredibly thin, only a few tens of meters thick in most places. They are composed of countless icy particles, from dust grains to boulders the size of houses. These ice fragments glide in formation around Saturn's equator, billions of tiny moons tracing exquisite flat paths. From a distance, the rings look solid, like a disk or the brim of a hat, but up close, we appreciate their true nature. A shimmering, spinning cascade of ice and rock pieces, each orbiting on its own. Gaps in the rings, like the prominent Cassini division between the broad A and B rings, create distinct bands. These gaps are caused by gravitational resonances with Saturn's moons and by the presence of small shepherd moons that patrol the rings and herd particles out of certain regions. In places, we see wakes and ripples in the ring material, patterns caused by the tugs of moons like tiny pan embedded in the Encke gap, or by a recent disturbance such as a moonlet that broke apart. The rings shine bright, reflecting sunlight like a million little mirrors. Composed mostly of water ice, they are pristine and cold. How they formed is still debated. Perhaps a moon strayed too close to Saturn and was torn to pieces by tidal forces. Or maybe they are leftover debris from Saturn's formation that never coalesced because of those same tides. Whatever their origin, the rings are likely ephemeral on geologic timescales. Slowly, the particles will spiral down into Saturn or be lost to space. But for now, in our epoch, they make Saturn the crown jewel of the solar system. As we skim above the ring plane, the reflection bathes our ship in a soft white glow, and we can see the shadow of Saturn cast onto the rings like a dark band cutting across their brightness. Saturn has its own extensive family of moons, more than 80 known, ranging from giants bigger than Mercury to small tumbling rocks only a kilometer across. Foremost among them is Titan, Saturn's largest moon and the second largest moon in the solar system. Titan is a world that, if not for its parent planet, could be a planet in its own right. It is enveloped in a thick, orange, smoggy atmosphere, even denser than Earth's air. As we approach Titan, we see it as a hazy orange sphere, the only moon shrouded in clouds. This atmosphere is mostly nitrogen, like Earth's, but with a significant dash of methane and a cocktail of complex hydrocarbons. It completely obscures the surface, creating an ever-present reddish-orange haze. Beneath those clouds lies a frigid but remarkably Earth-like landscape, as discovered by probes and radar. Titan has weather, lakes, and rivers, but of liquid methane and ethane rather than water. In Titan's cryogenic climate, around 179 degrees C at the surface, water ice is as hard as rock, and it is methane that can exist as a liquid. Titan's sky likely drizzles rain of liquid natural gas at times, filling basins and carving river channels over the eons. Indeed, Titan sports lakes and seas near its polar regions, true lakes of methane, dark and reflective, some larger than North America's Great Lakes. The thought of standing on Titan is otherworldly. Under an apricot sky with methane clouds, one might hear the gentle lap of hydrocarbon waves on an icy shore. Gravity is low, Titan is smaller than Earth, and the air dense, so dense that humans could theoretically strap on wings and fly through its sky. But it would be a dim, cold flight under a salmon-coloured gloom. As our ship descends beneath Titan's cloud deck, in our imagination, the sunlight is weak, just a dusky reddish glow filtering through. We find ourselves above dunes of hydrocarbon-rich sand, sculpted by a sluggish, dense atmosphere. In the distance might glint a methane lake reflecting the dull daylight. It's a scene both alien and oddly reminiscent of Earth's deserts and shorelines, a testament to geology and climate working in parallel on two very different worlds. Titan, with its thick atmosphere and surface liquids, is unique. A laboratory of organic chemistry where complex molecules rain from the sky and accumulate in the sand. Some speculate that, in Titan's lakes or within its crust, primitive life could eke out an existence using liquid methane as a solvent instead of water. It's a long shot, but Titan sparks our curiosity about life's adaptability. Another moon of great intrigue is Enceladus, a tiny ice moon only about 500 kilometers across. We first notice Enceladus as a bright, white dot orbiting in the midst of Saturn's diffuse E-ring. It reflects almost all the sunlight that hits it, indicating a surface of fresh, clean ice. As we draw nearer, Enceladus transforms into a glittering snowball, crisscrossed by fractures and canyons. The most remarkable discovery about Enceladus is revealed at its south pole. As our craft flies over that region, we see geysers, enormous plumes of water vapor and ice, continuously erupting from long, tiger-striped fissures in the ice. These geysers shoot material hundreds of kilometers into space, feeding the E-ring and creating a huge, wispy halo of fine ice grains around Saturn. The source of these plumes lies beneath Enceladus's surface. Tidal interactions with Saturn heat its interior, and hidden below tens of kilometers of ice is a global ocean of liquid water. In effect, Enceladus is an icy shell encasing a warm ocean, with cryovolcanoes spraying some of that water out into space, where it freezes instantly into fine ice particles and snow. We marvel at the sight, dozens of geyser jets backlit by the sun, creating a shimmering curtain of ice crystals along the moon's limb. Flying closer, we could almost feel the fine mist hitting our ship. Indeed, a probe once tasted these fumes and found salts, organics, and even hints of warm temperatures, evidence of hydrothermal vents on Enceladus's seafloor. This little moon, only a few hundred kilometers wide, has become one of the top places of interest in the search for life. Beneath its ice, where the water is liquid and toasty, perhaps 90 degrees Celsius near vent chimneys, and minerals mix, conditions could be similar to the deep oceans of Earth, where life thrives around hydrothermal vents. It's a staggering realization. Enceladus, a tiny spark in Saturn's retinue, might harbor living organisms in its dark, subsurface sea. As we pull away, we watch its geysers spray on, unceasing, like a cosmic fountain against the starry backdrop, and we leave a part of our imagination beneath that ice, wondering. Saturn's other moons each carry their own stories. There is battered Mimas, small and heavily cratered, with one gigantic impact crater, Herschel, that makes it resemble the Death Star from fiction. There is Iapetus, yin-yang in coloration, one hemisphere bright ice, the other coated in dark material, and sporting a puzzling equatorial ridge that makes it look like a walnut. Rhea, Dione, Tethys, mid-size moons, are frozen worlds with ancient cratered surfaces, some showing hints of past internal activity in the form of chasms or streaks of fresh ice. Hyperion is a tumbling, spongy-looking rock, chaotically rotating as it orbits. And tiny Pan and Daphnis dwell within Saturn's rings themselves, sculpting the edges of gaps with their gravity and sending subtle waves through the ring particles as they pass. In total, Saturn's system is like a grand miniature solar system, each moon contributing to the story, whether through adding material to rings, clearing gaps, or resonating with others to maintain the dance. It's a complex, beautiful interplay of gravity and time. Hovering above Saturn's cloud tops, we take in a final panorama. The rings stretch out below us like a flat, glowing disk, casting a broad shadow onto Saturn's upper atmosphere, a dark band encircling the planet. Saturn's amber globe peaks above the rings, and we see the curve of its horizon and the delicate gradient of its cloud bands. Off to one side, a few pearls of light betray the presence of moons. Titan, with its orange atmosphere visible as a tiny sphere, and others merely points reflecting sunlight. The Sun, some 1.4 billion kilometers away now, is feeble, only about 1% the brightness we know at Earth. But still, it is the dominant light in the sky. In this soft illumination, Saturn glows serenely. The entire scene has an unreal, ethereal quality, as if we're observing a finely crafted cosmic jewel in a setting of black velvet. We linger, drinking in the elegance of Saturn's rings and moons for as long as we can. At length, we must continue. With a gentle nudge, our spacecraft departs Saturn, leaving behind the most iconic sight of our solar pilgrimage. As the rings thin to a line and then vanish from view, we are once more enveloped in darkness and quiet. We are venturing now into the true outer reaches, into the realm of the ice giants. Our next destination lies nearly twice as far from the Sun as Saturn. The sunlight will dwindle further, and night will dominate. In that far frontier, a blue-green world tipped bizarrely on its side awaits. Onward, we voyage to Uranus, the tilted ice giant skirting the edge of visibility. Another immense span of emptiness lies between Saturn and Uranus. When we finally arrive, we find Uranus drifting in deep twilight. From a distance, Uranus appears as a tiny aquamarine star, barely glinting against the black. As we draw closer, it resolves into a pale cyan orb, a smooth, featureless disk with only the faintest hints of white cloud bands. This is Uranus, seventh planet from the Sun, an ice giant about 4 times Earth's diameter, composed mostly of hydrogen, helium, and a higher proportion of water, methane, and ammonia ices. Its tranquil blue-green color comes from methane gas in the upper atmosphere, absorbing red wavelengths of sunlight. Uranus's face looks placid and uniform, almost placid, a sleeping giant with a calm veneer. Yet Uranus is extraordinary in one defining way. It is a planet turned on its side. While the other planets spin more or less upright relative to the plane of their orbits, Uranus's axis is tilted by a whopping 98 degrees. It practically lies on its side as it goes around the Sun. At some point in the deep past, something likely collided with Uranus and knocked it askew, forever changing its orientation. Now, Uranus behaves like a rolling ball in its orbit. For about a quarter of its 84-year journey around the Sun, one of its poles points almost directly at the Sun, while the other pole faces away into darkness. As a result, one hemisphere experiences 42 continuous years of sunlight, while the opposite hemisphere is mired in a 42-year night. Decades later, as Uranus reaches the opposite side of its orbit, the previously dark pole enjoys 42 years of light, and the other pole endures the long night. No other planet has such extreme seasons. Imagine standing near Uranus's north pole at the height of summer. The sun would hang low in the sky, circling around and around without setting for decades, bathing the icy landscape in an endless pale glow. Then, as Uranus moves on, the sun would sink toward the horizon and eventually vanish for an equally long winter. Near the equator, the pattern would be closer to a normal day-night cycle, but even there, the sun would take a highly tilted path through the sky, and the appearance of day and night would shift bizarrely over the course of the Uranian year. Uranus's sideways orientation makes it one of the strangest worlds we've encountered. In the frigid atmosphere of Uranus, where sunlight is only a few tenths of a percent as intense as at Earth, temperatures plunge to the lowest of any planet. The cloud tops are around 220 degrees. High-altitude haze layers and some methane clouds do exist, but they form only subtle banding and occasional small bright features. For a long time, Uranus was thought to be virtually featureless, a serene, pale globe with hardly any weather. And indeed, when Voyager 2 flew by in 1986 during Uranus's southern summer, it saw an almost uniform blue-green sphere. However, as the years passed and Uranus approached its equinox, when the sun shines on its equator, astronomers using improved telescopes and later instruments began to spot signs of activity. Faint cloud bands, a dark spot or two, and even extremely large storms blossoming in the atmosphere. It seems that as each hemisphere gets a taste of spring or fall after decades of extreme sunlight or darkness, Uranus's atmosphere stirs awake somewhat. Still, compared to Jupiter or even Neptune, Uranus's weather is subdued. Part of the reason may be that Uranus, alone among the giant planets, gives off very little internal heat. It's almost as if whatever collision knocked it over also let out much of its primordial warmth. Uranus's calm exterior, then, might reflect a colder, more sluggish interior. It hides its heart beneath a tranquil mask. Uranus is encircled by a system of delicate rings and a retinue of moons. In 1977, astronomers discovered Uranus's rings when the planet passed in front of a distant star. The star's light blinked on and off several times before and after Uranus obscured it, evidence of multiple thin rings. Today, we know Uranus has more than a dozen narrow rings composed of dark rocky chunks and dust. They are much fainter than Saturn's glorious rings, but they share a similarity. They lie in Uranus's equatorial plane. Because Uranus is tilted on its side, these rings are essentially vertical when viewed in the context of the solar system, like a giant hula hoop turned at a right angle. When Uranus's pole points toward the Sun, its rings are seen face-on from the Sun's perspective. When Uranus is sideways to the Sun, at equinox, the rings present an edge-on profile. As our spacecraft flies through the Uranian system, we look back and see the rings as fine, shimmering lines encircling the planet's middle. The widest and brightest is the epsilon ring, accompanied by several thinner companions. These rings are kept in line by small shepherd moons that confine the ring particles with their gravity. The rings of Uranus, while not as celebrated as Saturn's, add a subtle grace note to the planet, a reminder that even in the outer darkness, nature can craft structures of delicate beauty. Uranus boasts at least 27 moons, and they too orbit in the planet's tilted equatorial plane, meaning they follow Uranus's bizarre orientation. The major moons of Uranus are named after characters from Shakespeare and Alexander Pope, befitting the planet's poetic mystique. The two largest, Titania and Oberon, are around 1,500 kilometers and 1,200 kilometers across, respectively. They are worlds of rock and ice, heavily cratered, but not without interesting features. Titania has enormous valleys, One trench stretches nearly 1,600 kilometers long, suggesting internal forces cracked its crust long ago. Oberon's old surface is dusted dark by some material, and many craters on Oberon have bright ray systems of fresh ice, hinting that sometimes its subsurface ice is exposed by impacts. Closer to Uranus orbits Ariel, a bit smaller, which has the brightest surface of the bunch and shows signs of relatively recent resurfacing, perhaps through icy volcanism that flooded some areas with fresh frost. In contrast, Umbriel, similar in size to Ariel, is very dark, an ancient charcoal-hued body with little evidence of past activity beyond a strange bright ring on one crater floor, perhaps a deposit of frost from an internal eruption. And then there is Miranda, the innermost of the large moons, and one of the most bizarre-looking objects we've seen. Only about 500 kilometers in diameter, Miranda looks as if it was shattered and clumsily reassembled. It has regions of wildly differing appearance. One area might be saturated with craters, another nearly crater-free, but scored with enormous concentric ridges and troughs. Giant cliff walls. The tallest known is Verona Rupes, estimated at 20 kilometers high, scar Miranda's icy surface. It's possible Miranda was broken apart by a massive impact, and the pieces rejoined under their mutual gravity, or that tidal forces when Uranus was capturing other moons caused Miranda's interior to heat and convulse. Either way, Miranda is a jumbled world, showcasing one of the most dramatic topographies relative to its size. Each Uranian moon carries clues to the processes at play in the cold outskirts of the solar system. They orbit in near synchrony, locked in the same tilt as Uranus, so their poles and equators experience the same extreme seasons as the planet. One pole of each moon can languish in darkness for decades, then decades of light. What a stark existence that must be. Half a life spent under a low sun that circles the horizon, half under an almost starless sky. Uranus itself, perhaps a dim turquoise glow overhead. Coasting through the Uranian system, we feel a distinct quiet and loneliness. The sunlight here is faint. The sun is just another bright star-like point, illuminating Uranus about 1/400 as strongly as at Earth. Space itself appears inkier and more absolute. Uranus, with its ghostly blue tint, casts a feeble light on its rings and moons. The environment is cold beyond measure. Our spacecraft's instruments register the paucity of heat and the near absence of energetic activity compared to Jupiter or Saturn. Uranus seems to slumber in the depths, content to roll along on its side. And yet, there is a peaceful beauty in this celestial oddity. The symmetry of its rings, the ballet of its moons, the soft gradient of its hue, all offer a tranquil counterpoint to the turmoil of the inner solar system. We depart Uranus quietly, as if tiptoeing away so as not to disturb the planet's repose. Now our sights are set on the final planet on our itinerary, Neptune, the distant blue giant. It lies another 1.5 billion kilometers beyond Uranus, at the very frontier of planetary space. We have many billions of kilometers behind us since we left the Sun, and now only one more planet beckons. We brace for the coldest, darkest planetary destination yet, and wonder what marvels await us there. Finally, we arrive at Neptune, the 8th and outermost major planet. In this remote realm, nearly 4.5 billion kilometers from the Sun, Neptune appears at first as a dim blue star. Drawing closer, it blossoms into a magnificent azure globe, akin in colour to a calm ocean on Earth. Neptune is an ice giant, like Uranus, similar in size, about 4 Earths across, and composition, a mix of hydrogen, helium, and ices. But it quickly shows its own character. For Neptune is a dynamic world of supersonic winds and persistent storms, despite the feeble sunlight it receives. High in Neptune's atmosphere, thin wisps of white clouds streak over the blue background, methane ice clouds casting fleeting shadows on layers below. In 1989, a passing spacecraft in 1989 spotted a great dark spot swirling in Neptune's southern hemisphere, a giant storm system comparable to Jupiter's red spot. By the time we could observe Neptune with telescopes a few years later, that particular vortex had vanished. But later, a new dark spot appeared in the northern hemisphere. Neptune's atmosphere clearly breeds these huge tempests and then disperses them. Even now, as we watch, we might catch sight of a dark, oval storm forming or dissipating, and smaller white cloud systems, nicknamed scooters for their speed, zipping around the planet at high latitudes. This distant giant, despite receiving only about 1/900 of the sunlight Earth enjoys, boasts the fastest winds in the solar system, measured up to 2,000 km/h. These winds roar through the hydrogen, helium, methane air, driving storms around the planet in mere days. Some deep internal heat source within Neptune likely powers this raging weather, for the sun's light alone would be too meager. Neptune actually emits about 2.5 times more energy than it absorbs, hinting at residual heat or slow gravitational contraction, warming it from the inside and fueling convection. Neptune's atmosphere is a deep freeze. At the cloud tops, temperatures hover near 220 degrees, but the planet's internal energy fosters enough activity that Neptune is more visibly lively than Uranus. We see that midday on Neptune is dim, more like early twilight on Earth. The sun here is a tiny, brilliant point, not much larger apparently than a star, though it still outshines the full moon of Earth by many times. Under this faint sunlight, Neptune's clouds take on a vivid blue-grey colour. Occasional lightning flashes might light up the tops of thunderheads, and the tips of high clouds cast shadows on layers beneath, creating textured patterns across the bands. Neptune rotates in about 16 hours, and this quick spin stretches storms into elongated shapes and organizes cloud belts parallel to the equator. As Neptune turns beneath us, we glimpse the terminator, the line between day and night, sweeping across the atmosphere, and perhaps a bright auroral glow at the poles where Neptune's magnetosphere interacts with the solar wind. Surrounding Neptune is a subtle system of rings and arcs. When we align ourselves to see them backlit by the distant sun, a few narrow rings shine out. Neptune's rings are dark and dusty, much like those of Uranus, and arranged in clumps. Uniquely, parts of Neptune's rings form denser segments called arcs. It's as though the ring material is herded into uneven piles rather than uniformly spread. These arcs puzzled astronomers. Why wouldn't the ring particles distribute evenly over time? It turns out that small moonlets, tiny moons only a few tens of kilometers wide, gravitationally corral the ring particles, confining them to certain regions. Over long periods, the arcs may dissipate and reform. As of now, we observe a few distinct arcs in Neptune's outer ring, giving it a patchy appearance. Neptune has 14 known moons. The standout is Triton, by far the largest. As our craft swings toward Neptune's night side, we catch sight of Triton orbiting in a direction opposite to Neptune's rotation, a retrograde orbit. This fact tells us immediately that Triton is likely a captured object, not originally formed around Neptune. Triton is about 2,700 kilometers across, similar in size to Pluto, and shares many characteristics with Pluto, and other Kuiper belt worlds. A surface of nitrogen and methane ices, extremely cold temperatures, just about 235 degrees, and a thin atmosphere. When sunlight hits Triton's surface, a thin film of nitrogen frost sublimates into gas, forming a tenuous atmosphere that can condense back as the moon moves into Neptune's shadow. As Voyager 2 revealed, and our own close flyby now confirms, Triton is not an inert ice ball. Its surface is young in many places, with relatively few craters. We see great smooth plains of what might be frozen nitrogen, punctuated by wrinkled ridges. There are strange landscapes that look like the skin of a cantaloupe melon, undulating, dimpled terrain that is unique in the solar system. And as we move over Triton's sunlit limb, we witness something astounding. Dark, geyser-like plumes erupting from the surface, rising 8 kilometers high before the particles drift downwind in the thin air. These are cryovolcanic geysers. Triton is spewing out nitrogen gas and dust from beneath its crust. Each plume originates from an area likely heated a bit by sunlight, causing subsurface ices to vaporize and burst out. The winds, such as they are in Triton's barely there atmosphere, blow the plume particles in long streaks across the surface, which we can see as dark deposits extending tens of kilometers from the vent sources. This active geology indicates Triton's interior might still be warm. Perhaps tidal interactions with Neptune, despite its retrograde orbit, produce some heat or radioactive decay in its core, or it could be residual warmth from its capture and the subsequent tidal flexing long ago. There might even be a subsurface ocean tens of kilometers down, insulated by Triton's icy crust. It's conceivable that Triton, like Europa or Enceladus, has an internal ocean, though likely slushy and mixed with ammonia to stay liquid at such cold temperatures. In any case, Triton is a world that clearly is still evolving. The vistas on Triton are likely surreal. If one stood on Triton's surface, under the dim sun, one might see Neptune, a huge blue-green disk hanging in the sky, since Triton is in a close 5-day orbit around the planet. Neptune would appear about 10 degrees across in Triton's sky, 20 times the apparent diameter of our moon from Earth. It would be a beautiful sight, that big azure orb illuminating Triton's icy plains faintly. The sky itself might be a pale pinkish hue from trace gases. With so little air, you could see stars even at midday. The temperature would be only a few dozen degrees above absolute zero. Every so often, perhaps, a distant eruption would send a plume skyward, its particles glittering in the sunlight as they drifted. It's a scene of quiet, distant wonder, the double sunlight of a starry sky and a nearby giant planet lighting an alien ice field. Apart from Triton, Neptune's other moons are much smaller, likely captured asteroids or fragments from collisions. Proteus, for instance, is the second largest, but was only discovered by Voyager 2. It's irregular and dark, about 400 kilometers across, heavily cratered, and with no signs of geological activity. Nereid follows a highly eccentric orbit far from Neptune, suggesting it too was captured or perturbed by Triton's arrival. Several others, Despina, Galatea, Larissa, and more, orbit closer in, many serving as shepherds for the rings. They are all tiny, potato-shaped worlds that stick close to Neptune's equatorial plane. Neptune, then, is a fitting outer sentinel among the planets, dynamic yet remote, beautiful but largely inhospitable, attended by a moon that itself hints at the worlds beyond. As we take our leave of Neptune, we acknowledge that we have reached the end of one journey. 4.5 billion kilometers from the Sun, we are at the outskirts of the planetary family we set out to visit. The Sun here is just a sharp star, albeit far brighter than the others. The sweep of Neptune's lonely orbit defines, in many ways, the boundary of what was traditionally considered the solar system. But our pilgrimage among the stars does not end here. Beyond Neptune's orbit lies the Kuiper belt, a distant swarm of frozen worlds and icy debris. In that remote region, Pluto, Eris, Makemake, Haumea, and countless smaller bodies circle the sun in the cold and dark, forging a link between the planets and the reservoir of comets. And farther still, almost a light year from the sun, a vast cloud of comets, the Oort cloud, marks the gradual end of the sun's gravitational dominance and the beginning of interstellar space. We know that the sun's influence doesn't abruptly stop at Neptune, but Neptune is the last stronghold of the major planets. As we gaze outward from Neptune's perch, we see infinite night sprinkled with distant stars. Our own sun is merely one of them when viewed from afar, a particularly bright star, but just a star nonetheless. We have journeyed from the sun's radiant core to the frozen fringe of its planetary realm. We have voyaged over 4.5 billion kilometers, experiencing extremes of heat and cold, light and darkness, discovering worlds both familiar and utterly alien. And yet, our voyage is not over. Far beyond Neptune, the cosmic ocean stretches onward. Our tiny spacecraft, powered by curiosity, will press forward into the unknown, out beyond the Kuiper belt objects, beyond the furthest whispers of the Oort cloud, and into the interstellar sea, heading ultimately toward the distant horizon of the galactic rim. The story continues, and so we venture on into the endless night, our pilgrimage among the stars, ever unfolding. Far beyond the orbit of the last known planet, Neptune, the sunshine grows weak and the sky deepens into endless night. Neptune's cerulean disk is now far behind us, indistinguishable from the darkness. The sun itself has diminished to a small, intense point of light, no longer dominating the sky, but merely adorning it. Around us, the star-studded backdrop has become more profound. The Milky Way's glow subtle, but ever-present. Out here, on the threshold of interstellar space, we embark on the next stage of our cosmic pilgrimage. The warmth and light of the sun have faded to a distant glow behind us, and ahead lies the outer frontier of our solar system. We drift onward through the dark, silent expanse, approaching a lonely little world at the edge of sunlight's reach. At first, Pluto was just a tiny speck of light in the distance, barely distinguishable from the background stars. As we draw nearer, that speck slowly swells into a disk, revealing hints of colour and pattern. We approach cautiously, letting our eyes adjust to the low light of this realm. The journey has been long to reach this outpost of the sun. Decades ago, before a spacecraft first flew by, Pluto was a mystery, an indistinct dot even in our most powerful telescopes. Now, here it is before us, an entire world suspended in the deep freeze of space, waiting to divulge its secrets. There is a sense of solemn anticipation as we come face to face with this distant orb that had, for so long, been merely a symbol of the unknown. In the vast darkness, Pluto emerges, a tiny, dim sphere illuminated by a sun no brighter than a pinpoint. Pluto is so far from the sun that daylight here is barely more than a perpetual twilight. Yet, in this faint glow, we can see the contours of an alien landscape. As we float closer, the dwarf planet's surface comes into view. Broad stretches of pale, frozen plains, interspersed with darker, rusty-hued regions. One particularly bright expanse, shaped faintly like a heart, gleams with the reflection of exotic ices. This heart-shaped plain is a basin filled with frozen nitrogen, carbon monoxide, and methane, volatile substances that on Earth exist as gases, but out here are solid ice. Surrounding it, the terrain darkens in places to a charcoal brown, where complex organic molecules, formed by ages of sunlight interacting with surface chemicals, coat the ice. This stark contrast of light and dark gives Pluto a patchwork appearance, as if painted by the cosmos in shades of white, orange, and black. This is a realm of eternal frost, where even the air can freeze and fall to the ground, and where temperatures hover near the coldest extremes known in the solar system. We descend gently toward Pluto's icy plains. Beneath us lies the vast, smooth region of nitrogen ice, the bright heart we glimpsed from afar, now spread out below like a frozen sea. The plain is so smooth in places that it appears almost young, as if resurfaced not long ago in geological terms. It is crisscrossed by subtle polygonal patterns, the telltale signs that the surface itself slowly convects, like a boiling pot, but on a timescale of millions of years. Here, ices can flow and creep imperceptibly, erasing old impact craters and renewing the surface. At the edges of the plains rise rugged mountains of water ice, towering peaks that loom on the horizon, their summits catching the weak sunlight. These mountains, with bases buried in frozen nitrogen and methane, are as hard as rock in the frigid environment. Some stand nearly 3 or 4 kilometers high, comparable to the Rockies on Earth. Yet they are composed of water ice so cold and strong it can support such heights. They have been sculpted by ancient processes we are only beginning to understand. We marvel at the notion that on Pluto, water is the bedrock and nitrogen is a flowing glacier. The silence here is absolute. There are no sounds of wind or running water, only the imagined creaking of ice under its own weight and the distant, faint thumps of the occasional ice rock falling from a cliff face. We drift over a colossal ice ridge and into a shadowed valley where the sunlight fades to near darkness and stars peek out even in midday. Above the surface, Pluto's sky is a deep, star-studded black, but with a delicate surprise. A tenuous atmosphere clings to this little world, forming layers of haze that catch and scatter the sunlight. When the sun sits low on the horizon, its rays filter through these thin atmospheric bands, painting the sky in faint hues of blue and gold. It's a blue not caused by a thick blanket of air as on Earth, but by tiny particles suspended high above. Particles born from Pluto's own gases, transformed by the distant sunlight. This ghostly atmosphere is mostly nitrogen, like Earth's, with a touch of methane. Near Pluto's closest approach to the Sun, some of the surface ice warms just enough to sublimate into gas, creating a thin envelope around the planet. Now, as Pluto recedes on its elongated orbit, much of that atmosphere is refreezing, falling softly as a nearly invisible frost. Still, in the twilight, we see evidence of what remains. Layered hazes extending dozens of miles up, each layer glowing softly as it catches the last rays of sunlight. The sight is ethereal, a pale halo encircling the dark globe, hints of blue haze above the horizon, gradually fading into the starry void. It feels miraculous that such a fragile atmosphere exists here at all, a tenuous blanket giving Pluto a momentary sky. Time itself seems to slow down on Pluto. The sun, only a tiny, brilliant dot in the sky, rises and sets here over the course of an entire week. A single Pluto day lasts about 6.5 Earth days, and the frigid night stretches on under the light of countless stars. If we were to stay here until Pluto completed one full circle around the Sun, we would wait 2.5 centuries. In that immense span of 248 Earth years, whole generations would be born and pass on our home planet. Here on Pluto, seasons are measured in lifetimes. Because Pluto's axis is tilted so extremely, over 120 degrees, it essentially rotates on its side relative to its orbit. This leads to seasons of extraordinary duration and contrast. At its solstices, one pole points almost directly at the distant Sun, while the other points away. That means one hemisphere endures continuous sunlight for decades on end, while the opposite hemisphere is cloaked in a night that lasts an equally long time. For year after year, the North Pole might enjoy a continuous, faint daylight, the feeble sun circling around the polar sky without setting, while the South Pole languishes in a long, unbroken winter night. Then, as Pluto moves along its far-flung path, the situation gradually reverses. In this slow dance of seasons, frost builds up in the winter darkness on one side of Pluto, and then sublimates away when that side finally tilts into sunlight a century later. It is an alien rhythm of time, almost impossible to experience directly. A reminder that on Pluto, patience is woven into the fabric of existence. As we gaze up from Pluto's surface, we cannot ignore the presence of its companion. Charon, Pluto's largest moon, hangs in the sky above one hemisphere, fixed in place, never rising or setting. Locked in an endless embrace, Pluto and Charon always show the same face to one another. They rotate together as if connected by an invisible rod, twirling about a mutual center of gravity that lies in the space between them. Charon is so large relative to Pluto, over half its diameter, that some call them a double dwarf planet. From Pluto's near side, Charon would dominate the sky, an enormous grey-brown orb about the size that 8 or 10 full moons would appear from Earth, hovering perpetually at the same spot above the horizon. Its surface is mottled with craters and chasms. We see a dark reddish cap staining Charon's north pole, likely a deposit of material captured from Pluto's escaping atmosphere, painting Charon with the colours of Pluto itself. In the pale light, Charon casts a gentle luminance onto the Plutonian terrain, as a larger, duskier version of our moon might. If we stood on the icy plains of Pluto at night, under a sky illuminated by Charon, our surroundings would be dimly visible in a soft, bluish-grey light. Across the distance, Charon's own subtle features blur, but one might discern large craters or cliffs if they looked long enough. The effect is hauntingly beautiful, a binary planet sharing a private glow in the solitude of space. Conversely, were we to land on Charon and look up, we would see Pluto filling a huge portion of the sky, locked in place, just as Charon is in Pluto's sky. From Charon's viewpoint, Pluto would hang there, unmoving, with one hemisphere forever visible. The bright heart-shaped expanse might shine back at us like a pale beacon amid darker patches. We might see Pluto's thin atmosphere as a faint haze ringing its silhouette when it catches the sunlight. Pluto would be a breathtaking sight from Charon, a half-lit globe, colourful and mottled, suspended against the blackness and the serene backdrop of distant stars. The two worlds, forever facing each other, as if gazing across the void, underscore the quiet companionship they share in this far-flung region. Pluto itself has a small retinue of additional moons beyond Charon, tiny ice-bound satellites with names like Nix, Hydra, Kerberos, and Styx. These little moons are irregularly shaped, mere fragments a few tens of kilometers across, tumbling end over end as they orbit the Pluto-Charon pair. In Pluto's sky, they would appear only as star-like pinpoints, drifting slowly over the years, too small to show a disk to the human eye. They are like sparks flung off from the main fire, perhaps pieces of an ancient collision that gave birth to Charon and the system of moons. The presence of these companions in Pluto's orbit reminds us that even in the most remote corner of the solar system, complexity and motion abound. Our brief visit to Pluto reveals a world that, despite its isolation and diminutive size, is rich with wonders. Who would have imagined ice mountains and possible glaciers on such a tiny sphere? The encounter challenges our assumptions about where geological activity can occur. In the far reaches of Pluto's surface, there are hints of strange ice volcanism, cryovolcanoes that may have once oozed slush and water from the interior. We spot, in passing, a great rounded mountain with a central depression, which scientists speculate could be an ice volcano that erupted ages ago, spilling chilled water mixed with ammonia or other antifreeze chemicals onto the surface, only to freeze solid in the cold. And beneath Pluto's frozen crust, some researchers suspect there might even be a hidden ocean of liquid water, kept from freezing entirely by the faint warmth of radioactive minerals and the insulating power of thick ice. Imagine an ocean in perpetual night, buried under miles of frost, sloshing slowly in the darkness. Even here, at the edge of the sun's influence, the possibility of something as dynamic as liquid water hints that this remote world is not a static, frozen relic, but a living part of our solar system's story. Before we depart Pluto, we take a moment to appreciate the panorama around us. The dome of the sky is almost black at noon, the sun a faraway spark almost indistinguishable from the brighter stars. Without a substantial atmosphere to scatter light, the stars here do not twinkle. They burn steady and clear. The Milky Way arches across the firmament as a magnificent band of light, far brighter than we see it from Earth. For here there is no air or stray glow to diminish it. If one were standing on Pluto's surface, the sight of that Milky Way, millions of stars shining collectively, would be a humbling reminder of how far from home we have come. Charon hangs above, Pluto's icy plains stretch out below, and overhead the universe reveals itself in all its glittering glory. In this moment, the isolation of Pluto feels profound, yet there is also serenity in its quiet, distant existence. This little world, once merely a point of light, has welcomed us with unexpected complexity and beauty. Reluctantly, we pull away from Pluto, leaving it to continue its slow orbit around the Sun, and turn our sights further outward. Beyond Pluto lies an even broader realm of icy remnants. The Kuiper Belt, a distant ring of ancient frozen bodies encircling the Sun. The Sun's domain opens into a great cloud of small frozen worlds. This region is like a vast ring-shaped attic of the solar system, filled with ancient remnants from its formation. Here, tens of billions of miles from the Sun, countless icy bodies quietly orbit in the cold and dark. Unlike the rocky asteroids of the inner solar system, these objects are made of frozen compounds, water, methane, ammonia, and other ancient ices, preserved in deep freeze for billions of years. They are the leftover building blocks that never coalesced into another planet. For decades, Pluto was thought to be a solitary oddity in the far darkness. Only in the late 20th century did astronomers begin to discover other icy bodies beyond Neptune, revealing that Pluto was just one of many, and that a whole belt of ancient objects awaited our recognition. Now, we know this region as the Kuiper Belt, home to a multitude of frozen worlds. We drift through this expanse, and at first it seems empty, an endless void punctuated by starlight. The distances are enormous, We could travel for days or weeks without encountering a single sizable object. Yet, gradually, our eyes adjust, and we begin to find them, one by one. The sun, now diminished to a faraway glint, still lends just enough light for these wanderers to reveal themselves as faintly illuminated specks against the black. We pass one, and then another. Some are merely a few miles across, dark and charcoal-coloured, scarcely distinguishable from shadows. Others are larger, reflecting a bit more sunlight, with surfaces that gleam dully with frost. Each world that we encounter has its own shape, perhaps a lumpy, potato-like form, battered by eons of impacts, or a binary pair gently orbiting each other as they circle the sun together. One such world we find is slightly larger in mass than Pluto, a dwarf planet named Eris. Currently, Eris lies near the far edge of the Kuiper belt, around 3 times farther from the Sun than Pluto is at the moment. It appears as a tiny, distant disk, but we know from studies that Eris is coated in bright white frost, likely a layer of methane ice that reflects sunlight like fresh snow. Eris has a moon of its own, a little companion named Dysnomia that orbits it in the darkness. This distant world, discovered in the 21st century, was a catalyst for rethinking what it means to be a planet. So significant was Eris's discovery that it led to Pluto's reclassification and the realization that there are many such substantial bodies out here. As we glide by Eris, we sense its solitude. The sunlight here is so faint that an object like Eris casts only the weakest of shadows. On its surface, a noon would look much like deep dusk on Earth, and the starry sky would be visible even at midday. Eris moves through its 65-year orbit in majestic silence, carrying its moon along, both of them locked in a remote journey around the sun. Not far beyond Eris, we come across another frozen sphere. Makemake. Makemake is slightly smaller than Pluto and has a reddish-brown surface, likely due to methane and ethane that have been chemically altered by sunlight to form complex organics. Named after a creation deity from Easter Island mythology, Makemake drifts serenely through the Kuiper belt, with one small moon tagging along, discovered years after Makemake itself. We imagine what Makemake's surface might be like under our feet, a ruddy plain of frozen hydrocarbons, silent under the faint sun. There is virtually no atmosphere. The horizon is sharp and black beyond the glowing ground. Makemake takes over 300 years to complete one orbit of the sun, and it has seen the sun's light wax and wane over long seasons none of us could observe in a lifetime. We press onward and soon come upon one of the strangest denizens of this distant belt, Haumea. Haumea is unlike any other known dwarf planet. It rotates astonishingly fast, spinning end over end on its axis every 4 hours. This rapid spin has stretched Haumea into an elongated shape, almost like an egg or a flattened football. When we catch sight of Haumea, we note its brightness. It has a crystalline water-ice surface that glints in the sunlight, perhaps the aftermath of ancient collisions exposing fresh ice. Haumea is accompanied by 2 small moons that orbit it swiftly, and even a faint ring of debris encircles it, discovered by observing how it momentarily blocks out starlight. Named after a Hawaiian goddess of fertility and childbirth, Haumea itself seems to have been born of a collision. Fragments of its icy body are thought to have been scattered, some becoming its moons and ring. If we could hover nearby, we would see Haumea's rapid rotation blur the distinction between day and night on its surface, daylight and darkness alternating in just a few hours. Any visitor trying to stand on Haumea would feel much weaker gravity at the equator than at the poles due to this spin, an alien sensation of variable weight. We leave Haumea marveling at the dynamism hidden in this far-off region, where even small worlds can have rings and dance to a frantic beat. All around us, the Kuiper belt stretches on. It's a bit like the asteroid belt, but on a grander scale and composed of different ingredients. The belt likely holds millions of objects over a kilometre in size, and uncountable smaller ones. Dust and pebbles left from the solar system's formation. Yet, unlike the densely packed asteroid fields of science fiction, the Kuiper belt is incredibly sparse. We can appreciate its breadth only statistically, by the occasional sightings of these lonely wanderers. Each is separated by vast voids, announcing their presence only by the sunlight they reflect, and for those we pass close by the gentle gravitational tug they exert. Every so often, we find ourselves passing an object that humanity has actually visited with robotic explorers. In 2019, after departing Pluto, the New Horizons spacecraft flew by a small Kuiper belt object called Arakoth. We recall the images it sent home. Arakoth appeared as two roundish lobes fused together like a reddish snowman drifting through space. This shape confirmed what scientists had suspected, that many Kuiper belt objects might be contact binaries, formed when two small bodies slowly merged in the primordial nebula. As we drift by the general vicinity of Arakoth's orbit, we imagine seeing a similar sight. A peanut-shaped body slowly tumbling end over end, tinted red by eons of cosmic radiation darkening the surface. Its two lobes, once separate, now joined, testify to a quiet union billions of years ago. On its surface, the gravity is so weak that a casual jump could send you flying off into space, never to return. Arakoth is utterly silent and still, unchanged since the dawn of the solar system. It has witnessed the sun's light from afar for longer than life has existed on Earth, yet it likely looks much the same as it did at the beginning. To behold such an object is to look back in time, to see a piece of the solar system's infancy preserved in a deep freeze. As we navigate this region, we also become aware that it is the breeding ground for some celestial visitors that occasionally grace Earth's skies. The Kuiper belt is the source of many short-period comets that return into the inner solar system at intervals of decades or a few centuries. These cosmic nomads usually reside here in cold storage, inert and invisible. But if the orbit of one is perturbed, perhaps by the subtle gravity of a giant planet like Neptune, or by a rare passing star, the object may begin a long, slow fall toward the sun. When that happens, what was once a dark, icy rock transforms into one of the most spectacular sights in nature. Approaching the sun, the comet warms, and its ices evaporate, releasing gas and dust that billow into a glowing coma and a trailing tail that can stretch for millions of miles. We envision a particular comet nucleus drifting quietly in the Kuiper belt, a frozen, irregular chunk a few kilometers wide, blackened by organic material on its surface. Right now, it is just another minor resident of this dark realm. But perhaps, centuries or millennia from now, it will be nudged onto a path that takes it inward. It might spend decades falling toward the inner solar system, eventually flaring into a beautiful comet visible in the skies of future Earth generations. In ages past, such events have happened. Comets like Halley's Comet likely spent the bulk of their existence in regions like this, venturing near the sun only briefly every few decades. When we see Halley's Comet appear in our skies every 76 years, we are witnessing the small portion of its life spent under sunlight. The rest of its time is spent here, far from the sun's warmth. The Kuiper belt cradles these potential wonders, preserving them until fate decides it's time for them to visit the inner solar system and enchant whatever eyes might be turned skyward. Gradually, as we continue outward, the encounters become fewer. We have traversed the thickest part of the Kuiper belt, roughly 30 to 50 times the Earth's distance from the Sun. At these distances, the Sun's gravitational hold still guides these objects in orbit, but they are only tenuously bound. The belt begins to thin out as we approach its outer fringes. We pass by a few scattered icy bodies that stand as sentinels at the edge of this realm. One of them is extraordinary. Sedna, which we find on a tremendously stretched orbit that carries it far beyond the main Kuiper belt. Sedna is currently about 80 or 90 astronomical units from the Sun, several times farther out than Pluto. But that is just a fraction of its full journey. At its farthest, Sedna will travel out to nearly 1,000 astronomical units, an almost inconceivable distance, taking more than 10 millennia to loop once around the Sun. Right now, Sedna is still coming in from the depths of space toward its closest approach, decades from now, but even at its nearest, it stays far beyond Pluto's orbit. Sedna's surface is a dark reddish color, similar to those of Pluto and Eris, likely coated in complex organic material. If we could land on Sedna during the height of its summer, when it is closest to the Sun would still only be a pinpoint, noticeably brighter than from Pluto, but still just a fierce star in a black sky. And when Sedna returns to the deep outer darkness at its aphelion, the Sun will be so faint that a person standing there might confuse it for a regular star. Sedna and objects like it form a bridge between the Kuiper belt and the next vast region beyond. They are messengers hinting at an unseen, spherical swarm of comets orbiting at the limits of the Sun's domain. As we bid farewell to the Kuiper belt, we recognize that we have reached a transitional space, the threshold between the relatively flat disk of the planetary system and the immense, diffuse sphere of comets that surrounds it. We now venture into the outermost realm of the Sun's influence, a region almost entirely conjectural. No telescope has yet directly seen these far-flung comets, yet compelling in its necessity. This is the Oort cloud, named for the astronomer who proposed its existence. Unlike the relatively flat plane of planets and the Kuiper belt, the Oort cloud is envisioned as a vast, spherical shell enveloping our solar system in all directions. It could stretch nearly half the distance to the nearest star, Alpha Centauri. Here, at distances tens of thousands of times farther from the Sun than Earth, the night and the void reign supreme. The Sun's light is barely discernible from the background stars. Yet its gravity, though greatly weakened, still holds a loose grip on trillions of small objects, perhaps 1 trillion or more, that drift in this darkness. Each of these objects is essentially a comet waiting for its cue. As we slip beyond the Kuiper belt, the sense of structure fades. We are no longer in a disk, but an almost boundless expanse. If the Kuiper belt was sparsely populated, the Oort cloud is practically empty by comparison, simply because it is so enormous. To picture the spacing, each icy comet nucleus in this cloud might be separated from its nearest neighbour by millions of miles. We could wander for months at high speed without encountering another solid body. In truth, even calling it a cloud is poetic. It's more like an enormous, diffuse swarm. But though the comets here are far-flung, they collectively form a system, gently bound by the Sun's distant tug. It's like a dandelion puff, with seeds drifting far apart, yet still originating from the same flower. We are moving among these metaphorical seeds now, but they are nearly invisible. Only with the Sun's faint light behind us can we sometimes catch the slightest glimmer of one. A tiny fragment of ice and rock, perhaps a mile or two across, reflecting a sunbeam weakly as it slowly tumbles. It is eerily quiet. The concept of day and night loses meaning. Out here, the sun is a pinpoint, and all of space is effectively night. The stars are as brilliant as ever, if anything, more steady and clear, since even the thin interplanetary dust of the inner solar system is left behind. We might feel truly in interstellar space already, yet we are still within the embrace of our sun's gravity. We are in the outer courtyard of the solar system, where the boundary between being part of our system and being an independent wanderer of the galaxy blurs. We imagine one of these distant cometary bodies up close. It is a dark, dirty snowball, its surface perhaps coated in a crust of organic material that has been chemically altered by cosmic rays over billions of years. Underneath that crust lies a treasure trove of primordial ice, water ice, carbon dioxide ice, dry ice, methane and ammonia ices, and more. In its current state, this little worldlet is inert and unremarkable, essentially a frozen time capsule from the solar system's birth. It has no tail, no glow. It is simply a cold lump among countless others. If we were to land on it, the gravity would be so slight that we could hop from one end to the other with ease. The stars would surround us on all sides, and the sun might be so faint that we could cover it with the head of a pin held at arm's length. Occasionally, however, the deep slumber of these objects is disturbed. The Oort cloud is not isolated from the rest of the galaxy, as our sun and its brood of planets and comets orbit the center of the Milky Way. They pass by other stars, weave through different regions of varying density, and endure the subtle tidal forces of the galaxy itself. Every now and then, perhaps every few million years, a star wanders relatively close to the sun, close in cosmic terms. It might skim the outskirts of the Oort cloud, its gravity sending a slight ripple through the cloud of comets. Even without a passing star, the combined gravitational pull of the entire Milky Way's disk can tug at these loosely bound objects. Most of the time, these influences are gentle, doing little. But sometimes, they are enough to nudge an Oort cloud object from its slow circular path and set it on a new course. Suddenly, that comet begins to fall, inexorably, toward the inner solar system, towards the sun that it has never before approached so closely. What follows is one of the grandest transformations in nature. After millions of years of drifting in darkness, the comet accelerates under the pull of the sun. It spends perhaps millions of years gradually picking up speed, for distances in the Oort cloud are so great. As it draws nearer to the planetary region, the sun's warmth starts to have an effect. The comet's ices begin to sublimate, turn directly from solid to gas, forming a tenuous atmosphere around the nucleus called a coma. Radiation pressure and the solar wind push on this expanding cloud of gas and dust, stretching it out into a luminous tail that can extend for millions of miles. By the time the comet reaches the vicinity of the inner planets, it may have a brilliant tail visible across the sky. A wanderer that spent most of its existence invisible in the cold now becomes a resplendent visitor, captivating any beings that might be there to witness it. Throughout Earth's history, such long-period comets have been recorded as omens and wonders, bright apparitions suddenly appearing in the heavens and then vanishing weeks later, not to return for thousands of years, if ever. Comet Hale-Bopp in the late 20th century was one such traveller. It came from the distant Oort cloud, shone magnificently in our skies in 1997 with two glowing tails, and now is on its way back out into the darkness, not to return for over 2 millennia. Perhaps it originated from a part of the Oort cloud we are now crossing, disturbed into a sunward journey long ago. Most Oort cloud comets will never visit the inner solar system. They will remain in this distant halo, orbiting silently. Some will be perturbed only slightly, changing their paths, but not enough to send them sunward. Others might even be lost from the sun forever, stolen by the gravitational pull of another passing star, set loose to drift in interstellar space as orphaned comets. In fact, the Oort cloud is not only a source, but also a reservoir that exchanges material with the galaxy at large. One of the great realizations of recent times is that objects can and do travel between stars. In 2017, astronomers discovered an object named Oumuamua that passed through our inner solar system on a hyperbolic trajectory, meaning it was not bound to the sun at all. Oumuamua came from interstellar space. It was likely an ejected fragment from another star's Oort cloud or planetary system that happened to wander into ours. It was followed in 2019 by Comet Borisov, an actual active comet with a tail, also on a one-way journey through our system. These interstellar visitors are rare glimpses into the connective threads between star systems. They hint that our Oort cloud too has likely sent comets to other stars. Perhaps some comet we see in our skies originated around another sun, and one of our Oort cloud comets might someday light up the skies of an alien world many light years away. The boundaries between the stars are not impermeable. At these far frontiers, there is a subtle mixing of material, a trading of cosmic stories between distant suns. As we push still farther out, the number of solar-bound objects dwindles further. We are approaching the limits of the sun's gravitational influence. Out here, at perhaps 100,000 astronomical units, around 1.5 light-years from the sun, an Oort cloud comet barely feels the sun's pull. The gentle tug of the galaxy itself, and of passing stars, is just as strong. This is essentially the edge of the solar system in a gravitational sense, the place where an object can easily be pried from the sun's grasp. We are nearly a light-year from the sun now, an almost unfathomable distance. To give one more sense of scale, the Voyager 1 probe, humanity's farthest traveller, would need around 30,000 more years to reach this kind of distance, moving at its current speed. And yet, in terms of the journey to the stars, even this distance is just a baby step. Alpha Centauri, the nearest star beyond our sun, is still more than 3 additional light-years away. We have 1 foot in interstellar space, and 1 foot still barely in the solar system's realm. At last, we reach a point where one can truly say we are leaving the solar system behind. One is reminded of the photograph taken by the Voyager 1 probe back in 1990, from well beyond Neptune, which captured Earth as a mere pale blue dot suspended in a sunbeam. From our current vantage, even that delicate blue pinprick is lost to view, drowned in the sun's distant glare and the infinity of space. If we turn around now, the sun is nearly indistinguishable from the myriad stars around us. All the planets we visited, Mercury, Venus, Earth, all the way out to tiny Pluto, are clutched invisibly close to that distant spark, utterly imperceptible from here. Ahead of us lies the vast gulf between the stars. We have crossed the threshold. This is the outermost shore of our sun's influence. Beyond here, our journey will no longer be measured in astronomical units, but in light-years. We bid a quiet farewell to the last icy stragglers of the Oort cloud. They will continue to orbit the sun for eons, until some are jostled, or until, one by one, they slip away into the galaxy. We carry onward, into the true unknown of interstellar space. The sun, now just another point of light behind us. The pilgrimage now enters a new phase, as we leave our solar family entirely and set out for the beckoning stars that have long waited, shimmering on the horizon of the night. Now we are truly adrift in interstellar space, the vast ocean between the stars. It is a realm that seems almost completely empty, a void where even the nearest specks of matter are light years apart. The vacuum here is more profound than any we experienced within the solar system. Imagine floating in a loneliness so complete that for billions of miles around, there may not be a single grain of dust larger than a pebble. Yet, this space is not completely featureless. The interstellar medium, as it is called, contains wisps of gas, mostly hydrogen atoms, so sparse that they would be a better vacuum than any laboratory on Earth, but spread through volumes so immense that collectively they form clouds thousands of light years wide. It also contains dust motes, microscopic particles of carbon, and silicates from long-dead stars drifting in the dark. And high-energy cosmic rays zip through this emptiness. Atomic nuclei traveling near the speed of light, launched by distant supernova explosions. These ghostly particles occasionally strike our spacecraft or our bodies, but we would never know it without instruments. In this deep night between the stars, the concept of direction becomes abstract. With no nearby planet or sun to orient us, up and down are meaningless. We roll slowly, taking in the panorama in all directions. The stars surround us as a faint mist of light, denser along the band of the Milky Way that wraps around the sky. Even the constellations we knew from Earth have subtly changed. Our shifted vantage makes nearby stars appear in new positions, distorting the familiar patterns into something subtly, hauntingly different. The Milky Way is our galaxy seen from within, a concentrated band of millions of distant stars. Out here, far from any planetary glare or atmosphere, it shines with an almost spiritual glow, a diaphanous river of starlight. We can see dark patches within it, where interstellar dust clouds block the light from more distant stars. Toward one direction, the Milky Way's center lies hidden behind thick clouds in Sagittarius, home to a hub of stars and a supermassive black hole far, far away. In the opposite direction, we gaze out toward the sparse outer edge of our galaxy, where stars thin out into the intergalactic void. Every pinpoint around us is a distant sun, and the sheer multitude of them is humbling. Without the sun nearby, the darkness takes on a new quality. Our eyes adapt to a permanent midnight, illuminated only by starlight. There is no day-night cycle here, only eternal night, decorated by the steady light of remote suns. If we could hear anything, of course space is silent, we might imagine the faint hum of the galaxy's background energy, the whisper of radio waves from pulsars, the distant echo of ancient supernova remnants. But to our ears, there is only silence. It's a silence so vast and absolute that it feels almost loud in its totality. The temperature in the shade of our spacecraft would be just a few degrees above absolute zero. Only the faint afterglow of the Big Bang, the cosmic microwave background, providing a whisper of warmth. In this profound solitude, one finds room for reflection. Away from any sun, in the almost spiritual hush of interstellar space, we are confronted with both the immensity of the universe and the smallness of our own being. Every tiny pinpoint of light around us is a distant sun, possibly with its own planets and perhaps life, yet separated by unfathomable distances. Floating here, the realities of our home world feel both insignificant and infinitely precious. We become acutely aware that everything we know, All of human history, every breath taken by every creature, happened around one of those pinpricks of light, now far behind us. And out here, beyond the comfort of that warmth, we feel a gentle melancholy and a stirring wonder. It is a humbling perspective, but not a despairing one. If anything, the darkness between the stars carries a serenity, a sense of the eternal. Our journey across this gulf connects us, in a way, to all things. The atoms drifting in space, the starlight from millions of suns, the invisible threads of gravity tying the cosmos together. In the face of the infinite, we feel a quiet acceptance of our place. Tiny, yes, but part of this grand tapestry of existence. Such thoughts come and go like faint whispers as we sail on. We allow them to wash over us, then gently refocus on the road ahead. Travelling through interstellar space, we start to appreciate the tremendous scale of our journey. Even moving at a significant fraction of the speed of light in our imagination, it takes years to traverse the gulf between the sun and its neighbours. At the speed of our fastest real spacecraft, this trip would take tens of millennia. We reflect on this as we drift. For all the advances of civilization, the stars remain almost unimaginably far. Yet here we are, crossing that distance effortlessly in our mind, propelled by curiosity and wonder. Every so often, the emptiness might be punctuated by something unexpected, a reminder that even the void can harbour secrets. Consider the possibility of a rogue planet, a world that has been ejected from its home star system and now wanders the galaxy alone. Astronomers believe there could be many such orphan planets adrift in interstellar space, cold and dark. As we journey, we allow ourselves to imagine encountering one. At first, it would be invisible, soaking in starlight, but reflecting almost none. Only our instruments, or a faint gravitational tug, might betray its presence. We approach this enigmatic object slowly. It's a Jupiter-sized planet, cloaked in perpetual night. Without a sun, its atmosphere is a frozen haze, perhaps hydrogen, helium, and methane forming a deep, cold sky with faint auroras triggered by cosmic rays. If it has moons, they too travel in eternal darkness, perhaps with ghostly glints, if they have ice on their surfaces, catching distant starlight. We glide past this silent giant. Maybe it retains a bit of internal heat left from its formation, which could drive a slow weather system, swirling clouds visible only in infrared. The planet gives off no visible light of its own. It's a black silhouette against the star field, discernible mainly by the way it blots out stars behind it as we pass. It's a sobering sight, a whole world, untethered, lost between the stars. We feel an urge to linger, pondering what it would be like to stand on such a world's surface, under a sky without a sun, only the faraway star glow of the galaxy overhead. But our journey calls us onward, and so we leave this lonely planet to its solitude, drifting on through its endless night. As we continue, time and distance blur. The stars that were once remote become imperceptibly brighter, very slowly. Those that were pinpoints begin to hint at disks as we draw nearer. The nearest star system beckons ahead, Alpha Centauri. We sense its presence as a slightly brighter glow than the surrounding stars. It is still just a star among many, but we know it is our target, the first port of call beyond our solar system. 4 years have passed for its light to reach this point in space. Now, after our long traverse, we finally begin to close that gap. Anticipation builds subtly within the calm. We are about to trade the emptiness of interstellar space for the vicinity of a new sun. The darkness around us ever so gently recedes, and a faint warm hue grows ahead. Starlight from our destination. We prepare to enter the realm of Alpha Centauri, leaving behind the cold interstellar night and approaching a system of living starlight once more. After traversing the immense interstellar gulf, we finally approach our destination, the Alpha Centauri star system. In the distance ahead, what appeared from Earth as a single brilliant star now begins to resolve into two distinct points of light, growing ever brighter as we draw near. Our long journey through darkness is rewarded with the sight of not one, but two new suns shining before us. There is a sense of cosmic landfall, as if after sailing a lightless ocean, we've sighted a new shore of light. The void around us gradually brightens. Starlight, that was once merely a distant beacon, now becomes a warm presence. We are entering the domain of another sun. Alpha Centauri is the Sun's nearest stellar neighbour, a system of multiple stars bound together by gravity. As we draw closer, we see the two primary stars clearly, Alpha Centauri A and Alpha Centauri B, circling each other in a stately cosmic waltz. Alpha Centauri A is a golden white star, strikingly similar to our Sun, just slightly larger and more luminous. Its companion, Alpha Centauri B, is a bit smaller and cooler, shining with a soft amber tint. They orbit a common centre between them, swinging around each other once roughly every 80 years. At times they are farther apart, at their furthest, about as separated as Pluto is from our Sun. At other times, at their closest, only a few billion miles divide them, roughly the distance from our Sun to Saturn. Right now, from our viewpoint, they appear separated by a modest gap, both blazing in the darkness. We position ourselves somewhere equidistant from them, admiring the double sunrise that would greet an observer here. Two brilliant orbs hang in space, one a touch whiter and brighter, the other more golden orange. Their light intermingles, casting a combined glow across the void. We imagine what it might be like on a hypothetical planet orbiting Alpha Centauri A. The sky would have not one sun, but two. Alpha Centauri A, the primary, would beam down strongly, its daytime illumination not unlike Earth's. Alpha Centauri B, though smaller, might be visible in the daylight as a second, intensely bright point, or tiny disk, of golden light. During the planet's day, you might see two shadows, one crisp and cool-toned from the primary sun, and a second, fainter one, with a slight orange hue cast by the secondary sun. As the smaller star sets, its shadow would fade, and the landscape would briefly be lit from an odd angle by a dwindling amber light. When night finally falls, once both suns have set, the concept of night would be different, shorter, and with a lingering double twilight if one star sets shortly after the other. On such a world, sunrises and sunsets could be double features. A soft amber dawn from the secondary star, followed by the brilliant golden morning of the primary. And in the evening, a grand sunset of the main sun would still not plunge the world into full darkness until the secondary star, like a second smaller sun, also dipped below the horizon. It would be a world of two dawns and two dusks, every day a subtle light show of twin star interplay. To an observer floating in space within the Alpha Centauri system, the view is mesmerizing. Alpha Centauri A and B blaze near each other, like a pair of brilliant jewels in the black. Their combined radiance is strong enough that from Earth's distance they appeared as a single beacon, the third brightest star in our night sky. Only here, up close, do we fully separate their identities. We watch as these two stars move in their orbit, slowly, imperceptibly shifting relative to one another as years pass. It strikes us that our sun, which we left behind, is just another star of similar type. If it were here beside these, it might form a triple of golden suns. Indeed, many stars in the galaxy are found in multiple systems like this one. Our solitary sun is somewhat of an outlier. Here we see what is perhaps a more common arrangement, a stellar family rather than a single star. Yet, the Alpha Centauri family has more members. Farther out, so distant that it takes over 500,000 years to complete an orbit around the central pair, lies a small, red dwarf star, Proxima Centauri. Proxima is actually the closest individual star to our Sun, slightly nearer to us than the bright pair of Alpha A and B. However, it is so small and dim that from Earth it cannot be seen without a telescope. We turn our gaze to seek it out. At first we see nothing but the velvet black of space spangled with distant stars. Then, using sensitive instruments, or perhaps an enhancement of our vision, we pick out a tiny ember of a star glowing red against the void. Proxima Centauri's light is humble, more like a deep red twilight than a noonday sun. If we draw nearer to this little star, we notice it is restless in its own subtle way. Red dwarfs often flare unexpectedly, and Proxima occasionally brightens as magnetic storms on its surface erupt, sending out bursts of radiation. This unassuming star harbours at least one planet that we know of, Proxima Centauri b, a world only a little more massive than Earth, orbiting in what could be the star's habitable zone. Intriguingly, the nearest known exoplanet to our solar system is indeed this Proxima Centauri b. It resides at just the right distance from its dim star that liquid water could exist on its surface, if conditions are right. The very fact that our nearest neighbouring star has a planet of roughly Earth's size sparks the imagination. What would it be like on that world? The planet hugs its star closely, completing an orbit every 11 days, which likely means one side of the planet faces eternal day, while the opposite side is locked in endless night. Whether this world could truly be hospitable is unknown. Proxima's frequent flares might strip its atmosphere or bathe it in harsh radiation. But we can't help but wonder. If one could stand on the surface of that distant planet, perhaps in the gentle borderland between its day and night sides, the sky would be dim and red. Proxima would hang overhead as a coppery sun, far larger in apparent size than our sun looks from Earth, but giving off a murky, ruddy light. In that alien sky, one might also see two far-off lights that never twinkle, Alpha Centauri, A and B, as twin morning stars or evening stars, gleaming bright white gold in the twilight. They would be distant, but likely bright enough to cast a faint double shadow on the ground. It is a sky no human has ever seen, except in our dreams. A red sun, casting a dim glow on a rocky landscape, with two brilliant starry jewels lingering off to one side, heralding that even here, near this tiny red sun, we are in a system of multiple suns. What are the chances that life could exist in such a setting? Proxima b endures a harsh environment, constant stellar flares, and the gravitational lock of one hemisphere to its star. Yet the possibility tantalizes us. Perhaps in the planet's permanent twilight belt, where day meets night, some form of life could eke out an existence sheltered from the worst flares. And around Alpha Centauri, A or B, though we have yet to confirm any planets, it's possible that smaller Earth-sized worlds are there, eluding our detection so far. It's enticing to imagine that an Earth-like world could orbit one of those suns, bathed in twin sunlight. Future generations might find a second home there. For now, these thoughts remain speculation, but being here in the Alpha Centauri system makes them feel almost tangible. The nearest stars to our Sun offer a promise that other familiar havens might exist within our reach, if we can only find or visit them. We take a moment to simply bask in the light of these alien suns. After the long, cold night of interstellar space, feeling the warmth, even if only in imagination, of a star again is deeply comforting. Alpha Centauri A's rays on our face would feel very much like the sun's back home. The star's spectrum and colour are nearly the same as our sun's, so its light appears soft, white gold, and familiar. For a moment, we could almost pretend we are back in our own solar system, until we notice Alpha Centauri B also shining in the sky, reminding us this is a foreign place. The experience underscores a profound realization. The ingredients of the cosmos repeat themselves. Here is a sun-like star giving off life-sustaining light, an orange companion dancing attendance, and even a tiny red dwarf on the fringes with a possible Earth-sized planet. Systems like this might be common throughout the galaxy. Who knows how many of them have planets with life, or moons with oceans, or vistas that would steal our breath. Standing in the glow of Alpha Centauri, we feel an emotional connection across space. Our sun has siblings of a sort, and we have truly found another sun's shore to explore. At length, we prepare to continue onward. We bid goodbye to the triple star system of Alpha Centauri, carrying with us the light of two suns in our memories, and the conviction that the nearest stars to our sun are vibrant and dynamic places. As we move away, the two bright stars gradually draw back into a single point from our perspective, and Proxima's faint ember fades into darkness. We have taken our first step into the broader galaxy, and it greeted us with a splendid vision of multiple suns and the tease of new worlds. Our journey, however, does not end here. Ahead lies the rest of our local stellar neighbourhood, an assortment of other nearby stars that surround our sun in its galactic district. With Alpha Centauri now receding behind us, we turn to look outward at the wider community of stars sharing this small corner of the Milky Way. Alpha Centauri is our nearest star system, but it is just one member of a cadre of stars in our vicinity. Our sun dwells in a sparse neighbourhood, a kind of celestial small town within the vast metropolis of the Milky Way. Scattered within about a dozen light-years of us are several dozen stars and star systems, each with its own story. Some are bright and prominent. Many more are dim and easily overlooked. We cast our view around from our vantage point here, imagining visiting these neighbours one by one. Only a couple of light-years beyond Alpha Centauri lies Barnard's star. At nearly 6 light-years from the Sun, Barnard's star is the next closest individual star after the Alpha Centauri trio. It's a red dwarf, too faint to be seen with the unaided eye, but well known to astronomers. Barnard's star is small, with less than 15% of the Sun's mass, and it glows a ruddy red. If we were to visit it up close, we'd find a feeble star that provides only a dim, dusk-like light to any nearby space. Barnard's star holds a distinction. It has the fastest apparent motion across Earth's sky of any star, a sign of both its closeness and its high velocity relative to us. Over human lifetimes, it travels noticeably against the background stars. In the 1960s, there were tentative and later disproven claims of planets around it, which only heightened its intrigue. In recent years, Astronomers did find at least one planet, likely a frozen super-Earth, orbiting Barnard's star, far from the weak warmth it offers. We imagine flying into the influence of Barnard's star and seeing its dim cherry-red disk growing in size. Around it, the darkness remains dominant. This star would cast only a gloomy, rust-coloured daylight on any nearby world, a far cry from the cheer of our sun. And yet, Barnard's star is one of our closest companions in space, steadily moving past us on its own path around the galaxy. All around, the vast majority of the Sun's nearest neighbours are similar to Barnard's star. Faint red dwarfs, the smallest and most numerous type of star in the galaxy. There is Wolf 359, another red dwarf about 7.9 light-years away. So dim it's barely above the threshold of visibility, even with a telescope. Wolf 359 is so faint that if you were floating near it, you might have difficulty reading by its light. There is Lalanda 21185, a red dwarf at around 8.3 light-years, one of the brightest red dwarfs in Earth's night sky, though still far too dim to see without optical aid. It too likely has planets of its own, detected through the subtle wobble of the star. These red suns, emitting only a few % or less of the sun's light, outnumber brighter stars in our vicinity. In fact, of the 20 nearest star systems, the great majority are red dwarfs. They hide in the shadows, undiscovered by the naked eye, each quietly burning its fuel so frugally that it will outlast stars like the sun by many trillions of years. If any of them have planets, and if some of those planets host life, those life forms might gaze at a sky where our bright sun is just a modest star among many, perhaps not even noticeable without careful study. While the dim red dwarfs dominate in number, a few brighter beacons punctuate our local region. There is Sirius, a dazzling luminary just 8.6 light-years away. Sirius is the brightest star in Earth's night sky, a hot white-blue star, roughly twice as massive as the Sun, and about 25 times more luminous. Even at nearly 9 light-years, its brilliance outshines all other stars as seen from Earth. As we approach Sirius in our imagination, its radiance becomes blinding, a fierce white point that overwhelms the eyes. Sirius is relatively young, only a few 100 million years old, and it has a secret, a small, dense companion called Sirius B. Sirius B is a white dwarf, the collapsed core of a star that has already lived out its life. This dead star is about the size of Earth, but nearly as massive as the Sun, an extremely dense ember of carbon and oxygen. It orbits Sirius A at a distance comparable to Uranus's orbit around the Sun, completing a circuit every 50 years. Though Sirius B is invisible to the eye, lost in the primary star's glare, it's awe-inspiring to realize that one of our nearest stellar neighbors is not one star but two, one shining in the prime of life, the other a ghost of a star that died. We picture ourselves at a vantage point within the Sirius system. Ahead, Sirius A blazes blue-white, and off to the side, if we could block out A's glare, we might glimpse Sirius B as a tiny, fiercely bright pinprick, an almost spiritual reminder of the cycle of stellar life and death. It's a scene of vitality and remnants coexisting in one system. A little farther out, at 11.4 light-years, lies Procyon, another brilliant star, prominent in Earth's sky. Procyon is the brightest star in the small constellation of Canis Minor and part of the winter triangle asterism. It is a white-yellow star, somewhat larger and hotter than the Sun. Like Sirius, Procyon has a hidden companion, a faint white dwarf orbiting it every 40 years. Though Procyon's white dwarf is too dim to be seen directly, its presence was detected by its gravitational tug on Procyon. It seems our local neighbourhood is sprinkled with these stellar remnants, quietly orbiting their brighter partners. We contemplate the Procyon system and imagine the scene. A warm, bright star, similar to our Sun, with an unseen tiny partner circling at a distance. An old, collapsed star that long ago was likely more like an orange subgiant before shedding its skin. These binary systems of living and dead stars are reminders that our neighbourhood has witnessed countless generations of stars over cosmic time. 10.5 light-years away, we find Epsilon Eridani, a youthful orange star, a bit smaller and cooler than the Sun. This star, famous in science fiction as the potential host of the fictional planet Vulcan, indeed has at least one confirmed giant planet and a ring of dusty debris encircling it. Epsilon Eridani is only a few 100 million years old, practically a toddler compared to our 4.6 billion-year-old Sun. We can imagine its planetary system as one still settling down. Frequent comets and asteroids crashing into young planets, dust and gas still gradually coalescing or clearing out. Visiting it would be like seeing a version of our solar system in its infancy. At nearly 12 light-years, Tau Ceti quietly shines. Tau Ceti is very much like a twin of our Sun, slightly smaller and less luminous, and notably stable. It hosts a rich system of planets. Astronomers have detected at least 4, possibly 5, including some super-Earths that orbit at distances where liquid water could exist. However, Tau Ceti also appears to have an extensive disk of debris, far more comets and asteroids than our solar system, which could make its planets subject to frequent impacts. Still, Tau Ceti has long captured human imagination as one of the nearest Sun-like stars with a chance of harbouring life. And the list goes on. Multiple other stars glimmer in our vicinity, each with its own nature. There's 61 Cygni, a binary system of 2 orange dwarfs about 11.4 light-years away, notable as the first star system whose distance was successfully measured from Earth in the 19th century, giving humanity its first glimpse of how far away the stars truly are. Nicknamed the Flying Star for its swift motion across the sky, 61 Cygni's 2 K-type stars take centuries to orbit each other in a leisurely gravitational dance. At almost 13 light-years out is Captain's Star, an ancient red subdwarf more than twice the age of our Sun. It was born in a different part of the galaxy and now wanders near us. 2 planets have been discovered around Captain's Star, one of which orbits in the star's habitable zone, a tantalizing hint that even some of the oldest stars in our neighbourhood could host worlds with conditions for liquid water. There's Ross 154, a dim red dwarf about 9.7 light-years from us, which flares occasionally with sudden increases in brightness. And there's Ross 248, another faint red dwarf around 10.3 light-years away, moving in such a way that it will actually become our closest star in about 36,000 years. We also find ultra-cool brown dwarfs like the pair discovered only in 2013 about 6.5 light-years away, in the constellation Vela. So faint that they were invisible until modern infrared telescopes detected their weak glow. One of them has a temperature only a few 100 degrees above absolute zero, more akin to a hot planet than a star. Another object, detected in 2014 around 7 light-years away, is a solitary brown dwarf so cold, perhaps around 50 degrees, that it's not much warmer than Earth's polar regions. These are failed stars, objects with insufficient mass to ignite sustained fusion. They bridge the gap between planets and stars. They lurk invisibly in the darkness, and only with sensitive instruments did we realize our Sun had more of these stealthy neighbors than anyone suspected. All told, within a radius of about 10 light-years from Earth, there are roughly 15 to 20 star systems, containing around 30-odd individual stars when you count multiples. Stretch that radius a bit further to 15 light-years, and you encompass perhaps a few dozen systems. It's a tiny drop in the cosmic ocean, and yet even within this drop, we see astonishing diversity. Bright young stars, elderly fading stars, multiple star arrangements, tiny red dwarfs barely fanning embers of fusion, dead white dwarfs, and planets of all sizes and kinds. Our Sun sits among this collection as a fairly ordinary member. If an astronomer around a planet of another star were cataloguing neighbours, our Sun might not particularly stand out, except perhaps to note it's solitary and of medium brightness. From the perspective of, say, Sirius or Alpha Centauri, our Sun would appear as a moderately bright star in the constellation Cassiopeia or Monoceros, unremarkable to all but the most careful observer. This realization is humbling. Out here, our home star is just one more pinpoint of light. Though the distances between these neighboring stars are vast, they are still bound together in a loose way. All these local stars, including the Sun, orbit around the center of the Milky Way galaxy, taking roughly 230 million years to complete one grand circuit. As they do, they bob slightly above and below the galactic plane and drift relative to one another. Our Sun and its current neighbors are moving through a region of space known as the local bubble, an extended volume of hot, very low-density gas, likely blown out by ancient supernova explosions. This bubble provides a kind of cavity in the galaxy's interstellar medium, which is why the interstellar gas around here is so tenuous. Inside this bubble, our local stars share a similar environment, and for a time, a similar journey. Of course, on the scale of millennia and millions of years, the configuration of our stellar neighborhood slowly changes. Stars like Barnard's star move steadily across the sky, and in tens of thousands of years, the map of nearby stars will look different. Some neighbors will have moved on, others will drift nearer. But at this moment in cosmic time, these particular stars form our Sun's community. Pausing here, we take stock of the journey. We have now travelled from the Sun's familiar neighbourhood out into the surrounding wilderness of stars. We passed the outer planets and dwarf planets, crossed the Kuiper belt, and ventured through the far-flung Oort cloud into true interstellar space. We arrived at the nearest star system and then continued outward to meet the other suns in our vicinity. In doing so, we've come to see our Sun in context, one among many, neither the brightest nor the dimmest in its locality. Our pilgrimage among the stars has revealed that even within just a dozen or so light years, the universe offers an incredible variety. We feel a sense of kinship with these stars. They are our cosmic neighbors, the companions of our Sun's journey through the galaxy. And yet, we also feel the enormity of what lies beyond. For as plentiful as the nearby stars are, they represent but a minute fraction of the Milky Way. Beyond the bounds of our little neighborhood, the galaxy stretches on and on, filled with billions of stars we have yet to approach, each system with its own wonders. Our cosmic pilgrimage through the Sun's neighborhood leaves us with quiet revelations. We have seen that our home star, once the center of our universe, is but one spark in a great tapestry. We have felt the immense solitude of space and discovered the companionship of neighboring suns. We have touched other shores of starlight and found them both alien and strangely familiar. Each step of our journey has expanded our perspective, gently reminding us of the vastness we are part of. And yet, there is comfort in this enormity. The same natural laws and cosmic light connect us to every corner of the galaxy. we take a final, reflective look at the cluster of stars we call home. In the silent darkness, it is as if the universe itself is urging us onward, whispering that beyond every horizon, more awaits. Our path now extends beyond these local stars into the wider Milky Way. We have so far to go, but there is no need to rush. In this timeless void, we float with patience and wonder. When we are ready, we will let the subtle pull of curiosity guide us forward again. The stars ahead beckon us deeper into the unknown, and we will follow, one serene step at a time, continuing our pilgrimage among the stars. As we leave behind the familiar cosmic neighborhoods explored in our earlier journey, we drift onward into the deeper reaches of the galaxy. The darkness out here feels boundless, yet serene, punctuated by the soft glow of faraway stars. Our voyage continues at a gentle pace, carrying us ever farther from our sun, into realms of mystery and creation that await in the vast interstellar expanse. In this quiet pilgrimage among the stars, we find ourselves on the threshold of new wonders, where the very fabric of the galaxy begins to reveal its secrets. Far ahead in the darkness, a faintly glowing cloud appears, a stellar nursery, the cradle of new suns. These vast nebulae of cold hydrogen gas and dust are the birthplaces of stars. Some stretch across dozens of light years, drifting quietly in the galactic disk. Within their misty folds, gravity works its subtle magic, drawing wisps of gas together, compressing them over millions of years. In these hidden pockets, the seeds of stars begin to take shape. Deep inside the nebula, dense clumps of gas form and collapse, growing hotter and denser as they draw in more material. For ages, nothing is visible. The infant stars are swaddled in thick veils of dust. Yet slowly, as the core of a clump is squeezed by gravity, a faint warmth emerges. A protostar is born, hidden in darkness, its light still too weak to escape its dusty cocoon. Only infrared eyes could pierce this gloom, revealing the gentle glow of a baby star tucked within the cloud. As time passes, the protostar's core grows denser and hotter, until one day it ignites a new light. Nuclear fusion begins deep inside, and the baby star starts to shine, a delicate first light pushing back the darkness. The surrounding gas and dust glow softly, lit by the newborn star's energy. What was once invisible now emerges as a luminous beacon within the nebula, a star taking its place in the cosmos. Such nurseries rarely birth just one star. Like flowers in a cosmic garden, many stars blossom together, forming a loose cluster that lights up their natal cloud. In the Orion Nebula, for example, a group of massive young stars called the trapezium shines at the heart of the nebula. Their intense starlight carves cavities in the surrounding gas, sculpting fantastical shapes, pillars, ridges, and valleys of glowing nebula. All around them, hundreds of smaller stars are also coming to life, hidden in the swirling dust. In another stellar nursery, the Eagle Nebula, dark towers of gas and dust rise like ancient monoliths against the starlight. These are the famed pillars of creation, immense columns where new stars are forming inside their tips. They stand light years tall, yet are fragile and ethereal, slowly eroded by the radiant energy of nearby young stars. Within those shadowy spires, infant suns are just beginning to glow, their light barely seeping out from their dusty wombs. It is a scene of quiet creation, hidden within cosmic clouds. Long ago, our own sun was born in a similar stellar nursery, nestled among siblings in a cluster of stars. Over time, those siblings wandered away, leaving the sun to sail the galaxy on its own. Around each newborn star, a disk of leftover gas and dust may coalesce into planets, moons, and asteroids. In this way, entire solar systems emerge from the nebula's bounty, stars accompanied by worlds that will circle them for eons. It is within such cradles of creation that not only stars, but the seeds of life-bearing planets are sown. The stellar nursery is but one face of the nebulae that inhabit our galaxy. Nebulae, the cosmic clouds themselves, come in many forms beyond these cradles of star birth. Drifting between the stars, they are majestic, mysterious structures, each with a story to tell. We leave the nursery and venture further to explore the other nebulae, the cosmic clouds of mystery that adorn the Milky Way. Some nebulae shine with their own light, aglow in rich colours. In these emission nebulae, intense ultraviolet radiation from hot young stars energizes the gas, making it fluoresce in reds and pinks. Others are gentler reflection nebulae, which do not glow by themselves, but instead scatter the light of nearby stars. Often tinted blue, they are like cosmic fog banks, illuminated by starlight. Together, they form luminous tapestries in the sky. Cosmic clouds lit from within or by nearby suns, each a delicate swirl of colour against the night. Yet not all nebulae shine. Some lurk as shadows, dark nebulae that obscure the light behind them. These clouds of dust and gas reveal themselves only by silhouette. In the constellation Orion, a small dark nebula shaped like a horse's head stands out against a luminous backdrop. The Horsehead Nebula, a tiny knot of opacity amid glowing hydrogen. Elsewhere, great rifts of darkness, like ink spilled across the sky, are formed by vast lanes of interstellar dust blocking the Milky Way's starry glow. These silent, lightless nebulae are as mysterious as they are beautiful. Nebulae can also mark the end of stellar life. When a sun-like star grows old, it gently sheds its outer layers into space. The result is a planetary nebula, an expanding shell of gas that glows as the exposed core of the old star heats it. These nebulae often appear as rings or bubbles, symmetrical and hauntingly beautiful. The Ring Nebula in Lyra, for instance, is a perfect smoke ring of stellar material, and the Helix Nebula in Aquarius looks like a great eye gazing into the cosmos. Within each, a tiny white dwarf star remains at the centre, the last ember of the star that was. There are more violent nebulae too, the torn, glowing remnants of supernova explosions. When a massive star ends its life in a cataclysm, the debris is hurled outward, forming filaments and expanding clouds of hot gas. The Crab Nebula is one such remnant, a tangled web of luminous threads created by a star that exploded nearly 1,000 years ago. Its centre holds a rapidly spinning neutron star, a pulsing beacon energizing the cloud. In another part of the sky, the Veil Nebula drifts as wispy arcs of colour, shattered pieces of a supernova long past. These remnants are cosmic fireworks frozen in time, proof that even destruction can create something of eerie beauty. All these nebulae, whether nurseries or remnants, are interconnected in the grand cosmic cycle. The gas and dust expelled by dying stars enriches the interstellar medium, seeding new clouds that will birth the next generation of stars. From the ashes of old suns, new suns will spring forth, and from these glowing nebulae emerge the stars themselves, often not alone, but in families. Our journey now follows these stars as they group together into sparkling islands. The star clusters, islands in the cosmic ocean. We move onward, leaving behind solitary stars and drifting clouds. And soon, we encounter entire communities of stars bound together by gravity. These are star clusters, islands in the cosmic ocean, where dozens, hundreds, or even millions of stars shine together as one family. Against the blackness of space, a cluster appears as a concentrated sprinkle of light, a miniature galaxy of stars huddled in one part of the sky. Approaching one is like sailing toward a glowing archipelago amid a dark sea. Open clusters reside within the galactic disk and arms, often near the nebulae that gave them birth. They are smaller than their ancient counterparts, typically a few dozen to a few hundred stars, spanning less than 30 light-years. The stars in an open cluster are usually hot, blue, and young by stellar standards. Over time, these clusters gradually disperse, their stars drifting away into the galaxy over hundreds of millions of years. Perhaps the most beloved open cluster is the Pleiades, the Seven Sisters. On a clear night, one can spot this cluster as a tiny knot of 6 or 7 faint stars close together in the constellation Taurus. But with a small telescope or binoculars, dozens of stars come into view, a true family of stellar siblings shining in unison. The Pleiades is wrapped in a gauzy blue nebulosity, a veil of dust reflecting the starlight, which lends the cluster a mystical glow. These stars were born together, and for now they continue their journey through space side by side, a glittering congregation in the dark. There is another kind of star cluster, very different in character, the globular cluster. Globular clusters are nearly spherical swarms of stars, ancient and tightly bound. Each contains tens of thousands to millions of stars packed into a ball only a few hundred light-years across. The stars in globular clusters are old, many glowing with a red or golden light, the hues of aged suns. These clusters orbit the Milky Way from the outside, populating a vast halo around the galaxy. In fact, about 150 globular clusters are known to encircle our galaxy, like a glittering halo of bees around a hive. They are among the oldest structures in the Milky Way, relics of an era when the galaxy was young. Drifting inside a globular cluster would be like entering a stellar metropolis. In the core of such a cluster, stars are crammed incredibly close. The night sky from a planet in that environment would be ablaze with countless brilliant stars on all sides, far brighter and denser than anything seen from Earth. The nearest neighbours might lie only light months away, rather than light years. The combined glow of hundreds of thousands of suns would bathe the sky in a diffuse golden light. It might never truly get dark. The concept of night in a globular cluster would be a softer twilight filled with the glimmer of myriad stars. Gazing out from that crowded realm, the rest of the Milky Way would be a hazy glow at the edges, outshone by the cluster's own starry splendour. Now, leaving behind the clustered islands of stars, our pilgrimage turns toward the heart of the Milky Way. We journey inward, across thousands of light-years, toward the galactic core, the dense central hub of our galaxy. As we approach, the starry background begins to brighten. What was once a thin band of the Milky Way, seen from afar, now swells into a rich, crowded vista of countless stars. We are entering the crowded downtown of our galactic city, the radiant nucleus around which everything revolves. Closer and closer to the galactic center, we drift, and the star density becomes overwhelming. Within just a few light years of the core, millions of stars crowd into an incredibly small volume. Space, that in our neighborhood might hold only a handful of stars, now contains a teeming multitude. Their collective light forms a golden fog in every direction. Here, night is never truly dark. The sky would shine like a perpetual dawn from the countless stars surrounding us. We are in the Milky Way's central bulge, a dense sphere of stars at the galaxy's heart. Many of these stars are ancient, cool red giants, puffed up in their old age. Yet among them are also youthful, massive stars and exotic stellar remnants, a rich stellar zoo concentrated in a tiny region. The airless void here is alive with starlight and motion. Stars swing around the center on whirling paths like crowded city streets of light. The gravitational pull at the core is tremendous, shaping the chaotic orbits of these myriad suns. At the very center, an invisible powerhouse resides, a supermassive black hole known as Sagittarius A. It contains the mass of over 4 million suns crushed into a single point. This dark titan is silent and unseen. Not even light can escape its grasp. We cannot observe it directly, but its presence is revealed by the frenetic dance of stars caught in its grip. Some of those stars whip around the black hole at astonishing speeds, completing a full orbit in just a few years. Such motion betrays the intense gravity concentrated at one infinitesimal spot, the black hole's location. Sagittarius A itself lies quiet for now, a sleeping giant at the galaxy's core. Occasionally it awakens. A sudden flare of high-energy light signals that it has snatched up some drifting gas or dust. A swirling disk of hot material circles the black hole, faint and ghostly, slowly spiraling inward. This glowing accretion disk is the last light before matter vanishes forever into darkness. It forms a ring around the black hole's shadow, marking the hidden center of gravity. Here in our journey, we cannot see the black hole directly, but we feel its profound presence, a deep hush at the very heart of all this brilliant chaos, anchoring the Milky Way's core. Departing the crowded galactic core, we find ourselves at the beginning of great curving lanes of stars that spiral outward. These are the Milky Way's spiral arms, the majestic, swirling pathways of stars, gas, and dust that wind around the galaxy's center. From above, they would appear like the arms of a giant pinwheel. Within them, we will journey through alternating regions of starlight and darkness, following the galaxy's sweeping design as it unfurls before us. The Milky Way's spiral arms are giant stellar highways, each coiling gracefully around the core. Astronomers tell us our galaxy has 2 prominent arms and several lesser spurs. Our own sun lives on a minor arm called the Orion Spur, a peaceful side road between the larger Perseus and Scutum Centaurus arms. Now, as we journey through one of the major arms, we are surrounded by a stream of stars stretching ahead and behind. The arm is like a luminous river, countless suns glinting like grains of sand, interspersed with cosmic clouds and clusters that ornament the flow. Traveling within a spiral arm, we see that it is not a rigid structure, but a region of enhanced star formation and density. Here, clusters of young stars are common, and glowing nebulae mark where new stars are being born, lighting the path with diffuse pastel colors. Between these starry nurseries lie slightly quieter stretches, but the darkness is never absolute. The collective light of billions of stars ensures a perpetual soft glow. The arm gently curves, leading us ever outward from the galactic center. It feels as if we are on a grand celestial roadway, with bright stellar signposts guiding our way through the galaxy. Onward, we travel along the spiral arm until, gradually, the stars begin to thin. We have arrived at the outskirts of the Milky Way, the galactic rim, where the spiral arms taper off into the cosmic darkness. Here, the bright clutter of stars and nebulae dwindles. Looking inward, we can see the sweep of the spiral arms we have traversed, glowing as a faint band. Looking outward, few stars remain to greet us. Only the endless expanse of intergalactic space lies beyond. We have reached the edge of our galaxy's stellar ocean. At the galactic rim, the night sky grows emptier. The dense star fields that filled our view nearer the galactic center have thinned to a sparse scattering of suns. Here, at roughly 50,000 light-years from the center, we have reached the edge of the Milky Way's bright stellar disk. The galaxy does not end sharply, but trails off. A few solitary stars and distant globular clusters still roam out here, gravitationally bound, but alone in the vastness. The silence of space feels deeper. Between these last outposts of our galaxy lies more darkness than light. This is the frontier of our galactic home, where cosmic night begins to take over. Though the bright part of the Milky Way ends here, the galaxy's unseen halo reaches much further. Enveloping the disk is a vast, diffuse halo of invisible matter and a few stray stars, extending nearly 1 million light-years out. This halo, composed mostly of mysterious dark matter, exerts a gravitational pull that helps keep the galaxy intact. We cannot see the dark halo, but we sense its presence as a gentle gravitational field stretching beyond the last stars. It reminds us that even in apparent emptiness, the galaxy's influence persists far into the dark. Drifting at the edge, we also find that our galaxy is not entirely alone. Several small companion galaxies accompany the Milky Way, orbiting around it like tiny moths around a flame. The Large and Small Magellanic Clouds, for instance, are two irregular dwarf galaxies just outside our own, visible from Earth's southern hemisphere as faint cloud-like smudges of light. Out here at the rim, we could see them hanging off to the side, starry satellites containing millions of stars circling the Milky Way. They gently tug on our galaxy and exchange wisps of gas and stars, quietly interacting over billions of years. These companions are a reminder that even at the edge of our galaxy, we are still in the company of others, clustered in our small corner of the universe. Before we slip entirely into the void beyond, we pause at the galaxy's edge to sense the more subtle forces at work in our Milky Way. Not all of the Milky Way's structure is visible as stars and nebulae. There are whispers in the dark, galactic winds and magnetic fields, unseen but powerful agents that shape the galaxy's evolution. Here at the rim, under the vast, quiet sky, we take a moment to feel those elusive currents that flow through the cosmos. They have been with us on this journey all along, guiding and influencing the galaxy's grand design from behind the scenes. Invisible to our eyes, a steady galactic wind flows outward from the Milky Way. High-speed particles stream from the star-packed core into the halo. It is as if the galaxy breathes, a slow exhalation of hot, tenuous gas into intergalactic space. This wind is powered by the energy of many violent events, the collective blast of supernovae, and perhaps occasional outbursts from the central black hole drive material outward. In essence, Our galaxy is not static, but gently sending some of its matter back into the universe. Galactic winds are not always gentle. Some 2 million years ago, the Milky Way's core experienced a tremendous outburst, possibly a frenzy of starbirth or a feeding of the central black hole that blew vast amounts of gas outward. The relics of this eruption are still visible. 2 enormous lobes of hot gas ballooning above and below the galaxy's disk. Astronomers call them the Fermi bubbles. Each bubble stretches tens of thousands of light years. They shine faintly in high-energy light, a spectral afterglow of that ancient blast. These giant cosmic bubbles are a ghostly echo of our galaxy's capability for upheaval, evidence that the Milky Way can, on occasion, forcefully expel matter into space. Today, the core has calmed, and the galactic wind continues in a quieter form, a slow, outward breeze. This persistent wind still carries traces of the Milky Way's inner life outward, gas enriched with elements forged in stars. In its currents drift atoms of carbon, oxygen, iron, the seeds of planets and life, blown from the crowded regions of the galaxy into the emptier halo beyond. Over time, these materials mix into the intergalactic medium or fall back onto the galaxy, helping to complete the grand cycle of matter. The galactic wind thus serves as a cosmic gardener, pruning here, seeding there, and shaping the growth of the galaxy over eons. Threaded through all of this is another invisible force, the galactic magnetic field. Like a web of unseen fibers, magnetic field lines stretch across the galaxy, running through interstellar space and entwining the spiral arms. We cannot see them directly, but their effects are real. They gently steer the charged particles of the galactic wind and cosmic rays, and influence how gas clouds collapse into stars. The Milky Way's magnetic field is very weak, millions of times weaker than a household magnet, yet over scales of light years, it has a cumulative power. It helps shape the galaxy's structure in subtle ways, providing a kind of scaffolding for the interstellar medium. We find hints of the magnetic field's presence in observations. The way light from distant stars is polarized by dust grains aligned in magnetic fields, or how radio waves reveal vast, orderly patterns in the halo. In some galaxies, winds of gas seem to flow along magnetic channels. In the nearby Cigar galaxy, M82, astronomers saw the furious outflow from its starburst core, guided by magnetic field lines, like smoke rising along invisible rails. In our Milky Way, the magnetic field likely fans out in an X-shaped pattern above and below the disk, drawn outward by the galactic wind. Through these unseen lines of force, the galaxy's breath and its magnetic heartbeat work together, shaping fountains of gas and sculpting the lanes of dust within the Milky Way. These subtle forces, the galactic winds and magnetic fields, remind us that not all shaping influences are visible or rapid. Over millions of years, they gently modulate how a galaxy lives and breathes. They disperse energy and matter, govern the movements of gas, and knit the Milky Way together with threads of magnetism. Invisible and silent, they nevertheless play a crucial role in the cosmic tapestry we have been exploring. Now we drift beyond the Milky Way's furthest stars, fully entering the intergalactic medium, the silent sea between galaxies. We turn to look back and see our entire galaxy in one view. The Milky Way is now a delicate mist of light behind us, a pale disk floating in darkness. Its spiral arms and central bulge form a faint glowing whirl, a tiny island of hundreds of billions of stars suspended in an infinite void. There is a poignant beauty in seeing our home galaxy from afar, alone against the velvet black, its light a gentle beacon across space. Out here, space is almost unimaginably empty. The nearest star is not light years away, but whole galaxies away. The few atoms that wander this void are so sparse that each one drifts alone for meters before meeting another. Temperature loses its meaning when particles are so far apart. But the gas out here, though tenuous, can be heated to millions of degrees by shocks from galaxy collisions far away. Yet it is so thin, you would not feel any warmth. It is emptier than any vacuum we can create, a chill and silent expanse. This is truly deep space, quiet and still. For a moment, it seems we are utterly alone. But as our eyes adjust to the darkness, we begin to notice faint glimmers in the distance. These are not stars, but other galaxies, each a remote oasis of light. Far ahead, we see the Andromeda Galaxy, our Milky Way's sister, as a faint, elongated blur, a spiral like our own, but 2 million light-years away. Scattered around are smaller galaxies of our local group, and beyond them, countless more in every direction. They appear as tiny, dim smudges or barely perceptible specks, so far away that their combined light barely whispers to us. The intergalactic space is dark, yes, but it is not empty of wonders. It is the backdrop upon which all galaxies shine like distant lanterns. In truth, the galaxies are arranged in a vast cosmic web. Invisible filaments of gas and dark matter link galaxy to galaxy across unimaginable distances. We are floating in one of the immense voids between these filaments. The nearest filament, millions of light-years away, connects the Milky Way and Andromeda to other galaxy clusters. But here, in this quiet emptiness, those structures are imperceptible. We feel only serenity and solitude. The silence is profound, broken only by the faint hum of existence, the distant starlight, and the soft glow of the universe's background radiation that bathes all of space. And so, in this silent sea between the galaxies, our cosmic pilgrimage reaches a moment of reflection. We have journeyed from the gentle warmth of our sun's neighborhood, through nurseries where stars are born, and nebulae of every kind, past clusters of stars and the crowded heart of the Milky Way, along spiral arms, and to the very edge of our galactic home. Now we drift in the great dark beyond, cradled by the infinite. In this vastness, the Milky Way is but one luminous pearl in a necklace of countless galaxies. In the stillness of intergalactic space, we are reminded of the unity of all things. The atoms in our bodies were forged in ancient stars, carried on galactic winds, and distributed through space before finding their way to our sun and earth. We are made of the cosmos, and it is made of us. Our voyage among the stars has been a journey through ourselves, in a sense, tracing our origins in stellar furnaces and cosmic clouds. Under the eternal night, this realization brings a gentle comfort. We are not isolated, but part of the endless story of the universe. As we prepare to conclude this interstellar journey, we carry with us a profound sense of peace. The immense scale of the cosmos gently puts all the cares of the day into perspective. Floating here between the galaxies in the hushed darkness, we feel a deep and tranquil calm. The stars and galaxies continue their slow dance, as they have for billions of years, and will continue for billions more. We on our tiny blue world, orbiting a star in the Milky Way, can find solace knowing we belong to this grand cosmic tapestry. Our pilgrimage among the stars ends not with a finite conclusion, but with an open horizon, an infinite expanse that invites reflection and wonder. In this quiet moment, we close our eyes and feel the gentle embrace of the cosmos. The stars will continue to shine above, and the universe cradles us in its endless, tranquil night. We return home with hearts full of cosmic wonder, at peace under the eternal sky.